We're going to get started in about 5 minutes, but we'll do an introduction now. We're your session chairs. My name is Jose Hurtado. I'm at the University of Texas at El Paso.
I'm Abigail Freeman at JPL.
And I'm Alexia Kubis at Cornell.
So the way this works, you guys know how this works by now. We'll have blocks of 4 talks and then 20 minutes of discussion. And for the discussion, we'll ask the speakers to come up to the front and we'll do sort of panel style. Please ask questions. If you do, come up to the mic and introduce yourself with name and affiliation. And if anyone is online, submit questions over the chat. We'll ask the speakers to mic up in the couple of minutes before you come up on stage. Just go over to the side to our AV assistants and they'll set you up. And then please return the mic after your talk, since there's only 2 of them. Let's see. We'll give you a 2-minute warning when you're at sort of the 8 minutes for your talk. We'll have a cutoff at 10 minutes, so that way we stay on the expected timeline. We'll expect sort of everybody to follow the code of conduct for the meeting, and we ask that there's no live streaming or photography. And we did have a request to remind any Dvornik judges to please submit your judging scores before the end of the day. Anything I missed?
Candy?
Candy, yes. I hope everybody helped themselves to candy that Abigail sort of provided. A nice reward for being here so early in the morning. We've got about 3 minutes before the first talk. Does anyone have any announcements for the analogs community or anything they'd like to share with the group? Otherwise, we'll wait another about 2.5 minutes for our first speaker. And I just realized I can push this and like... We're counting how many of you there are. All right, we're going to get started. Our first speaker this morning is Michael Thorpe, and his talk is the Mars Sample Return Analog Sample Library.
All right. Good morning, everybody. This is definitely the dedicated crowd who made it here this morning. I tip my cap to everybody who made it for the first talk of this session. So today I'm excited to talk about the Mars Sample Return Analog Sample Library, ASL. And so this is a picture of our fearless NASA and ESA leaders cutting the ribbon to the ASL, which opened up in November. It's housed at the University of Oslo. Here is a QR code you can scan to actually start your request now. I'm going to kind of wet your whistle, if I will, with all the samples that you can request in the sample analog library now. and dive into them in a little more detail and kind of describe how we're going to supplement this in the future and kind of looking forward what it's going to be. So this is kind of the mission statement of what the ASL is. It's a jointly managed collection that provides a joint way to identify, acquire, and manage suitable analog samples that benefit the MSR campaign, but also importantly, for the wider scientific community, and then even more so for publication and outreach. I think it's important that, you know, us in this community continue. I mean, everybody's here early in the morning, so obviously you care about environmental analogs. But while we're waiting for MSR samples to come back and we're anxiously waiting for that, we can get excited about working with these samples in our hand right now too. So I think it's a really cool opportunity to work with something that looks analogous to what we might be expecting and kind of hone in on our techniques. So that's kind of the moral of the story, and I think we can carry that out into these public outreach and communication with the public. So this is kind of a continuation of the title side itself, because there's been so many great world scholars that have contributed to what's going on with this analog collection, and it kicked off with this rock sample team who's currently working on a publication to come out soon. And then it carried on further with the Mars Sample Return Campaign Science Group, and that's where kind of my role came into play. We had a sub-team that was tasked with evaluating kind of what the current collection is and how we can supplement that collection going forward. And so this is a geographic map showing kind of the distribution of the 5 samples that we currently have in the analog sample library. I like to highlight on this map that, you know, we're dealing with samples that are collected in this relatively small watershed, Jezero Crater on Mars, but we have to scour Earth and kind of really try to find locations on Earth that are suitable for an analog for Mars. So it just really speaks to the diversity of the samples that Perseverance is collecting. And I think that's pretty exciting to note. So I'll dive into each one of these today and let you know a little bit more about the details of them all. So our first one here, and I try to highlight here every kind of sample that we're trying to map to with the MSR cache that we have going on here. So our first couple samples are igneous analogs. And so the first suite is supposed to represent the Maz formation. And so these are microgravos. And to do that, our field team collected samples from the Columbia River basalts, particularly the Steens Formation. And so these are 16 million year old basalts. And we've got 2 different flavors of this sample. It was 350 kilograms total that's sitting in the analog library. One of them is an aphanitic basalt, and another one has these large plagioclase grains in it too. So you can request either of those samples. The next suite is, it's supposed to highlight the diversity of what's going on in the Crater 4 campaign here with MSR, and this is supposed to represent the Seta Formation. So now we're dealing with something fundamentally different, so we had to get something fundamentally different for the analog collection too. So here we have an olivine cumulate. We have about 150 kilograms, or no, actually 250 kilograms of this sample that is from one block of an olivine peridotite intrusion that's in Scotland. And this is about a 16 million year old olivine intrusion there. So pretty cool sample that's representing Seta there. Our next samples were our sedimentary samples, and here we are trying to capture kind of MSR samples from the FAN campaign here. And so we have sandstones that were collected in California. Particularly the field team was targeting these planar laminated fine sandstones with minimal compaction, part of the Ridge Basin. We got about 150 kilograms of sample that are sitting in the ASL currently from these. Some field notes that this rock reacted with acid in the field mildly, so it tells you a little bit something about the composition if you're requesting these samples. Our next set of samples here were also targeting the fan front samples, and so particularly kind of samples from Hazeltop and Bear Wallow here. These were also from California, and this was a steeply dipping brittle sandstone. We have about 120 kilograms of sample that is currently in Oslo available for collection. And then our last analog that is currently part of the library here is a Regulus sample. This was supposed to represent the Regulus sample that was collected by MSR. And so I was part of this field team that went to Iceland, and we kind of gridded out an area on top of this sand dune, or on the windward side of a sand dune here. And we sampled just the top little couple centimeters of the sample. And so we have almost 400 kilograms of sample that's currently available. And I think you'd be surprised taking 400 kilograms of sediment actually did not make that much of an impact on it. Couldn't even tell we were there. So it's not that much, but it was pretty heavy to carry. Okay, so this is how you can request the samples where we're all sitting down here as users. It's kind of showing you going from the field, and we're going to supplement this with future field sites too, but kind of taking the samples all the way from where they're going to be stored and distributed to kind of making sure that we're tracking all our field notes, any publications that are coming from this, and how you as a user can start to request this. Eventually, it's going to go to this ASL allocation panel, which is pictured here. This is half NASA and half ESA folks that are going to evaluate those requests that come in. It's going to be based on kind of this hierarchy of where the samples need to go first in terms of, supporting the project overall, the larger scientific community. And then again, I want to highlight public and outreach relations here. And I think that's something really important. And I've got to touch these samples, all of them in hand. And it makes that much difference seeing rocks in hand than seeing something that is going to come back later. So, I highly encourage the community to get involved with this. So far, there's been 2. I actually think it's up to 3 requests for this, but hopefully more after this talk, and I hope everybody's getting excited about it. So it's important to note that this collection was currently established when we were around the Three Forks Depot, and so we only had a certain amount of samples at that point, and the rock team was tasked. With really collecting textural and physical analogs that were going to serve for understanding how the tubes were open and how the rock inside them was going to be processed that way. So we've been tasked since we have 9 additional cores that have been collected to really look for compositional analogs. And the important thing that I think everybody in this room probably knows is that there's no perfect analog for Mars here on Earth. And that's what this radar plot is trying to show, is that perhaps we just try to tackle certain criteria. We're never going to get this perfect analog, which is impossible. But we can look for maybe geochemistry, mineralogy, or grain density or porosity. So those are kind of the way we're moving forward, is to try to tackle these different components. So our team came up with kind of a list of findings here, which I don't want you to have to read in person. I'll just tell you that the summary was that we're missing some sort of this mafic component for the sedimentary rocks. We prioritized looking at the sedimentary rocks first. We're going to go on to the next batch of samples next. We're also missing some key components that may be time sensitive and or sterilization sensitive, so alteration products. And so to supplement this, we have some field sites that are proposed for this upcoming 2025 field season. And I thought it would be pretty cool to highlight what those sites are to get you excited what might be a part of the analog collection coming forward. So this site is really interesting. This is in southwest Iceland off the Storlaxa River here. This is going downstream. This is going upstream. And then I'm going to show you a rock outcrop over here where we go up. This is some beautiful fluvial equestrian sedimentary rocks that I've been to Iceland now nine times to do field work, and I've never seen sedimentary rocks there before. And so these are really unique rocks that we came across. And it was a story of fire and ice, much like Iceland is. And so you started with lava that was forming. It was going downhill here, and then there was some fluvial and lacustrine activity during a hiatus of lava flows here. This is right on the ridge that's running up the center of Iceland. And then eventually you had the right component of lava coming back in again and cementing those deposits. And so they're rather friable, but they are really cool and interesting sedimentary rocks. And this is what they look like closer. You have fluvial, you have some larger class in here too, and then some kind of lacustrine rocks too. Another rock that I think is cool that's going to be supplemented this year is a matrix supported conglomerate. And this is super interesting. It's got a ton of serpentine in there. This is what it looks like in thin section. It's in northwest Italy, part of the Trino Hills formation there, and excited about adding these samples to the library too. And it wouldn't be a talk for me if I didn't have some sort of XRD plot up here. So I had to get a little science in here. And so we ran these samples on here. And I think it's kind of remarkable. I compared Gale Crater Chemin data to these samples that we ran in the lab. And I know it's a different section on Mars, but there's remarkable similarities. You can see clay, amorphous materials. For particularly looking at the Jezero Crater samples, we see serpentines here too. So I think there's a lot of exciting things that are going to be added to the ASL coming forward. I'm excited to keep working on it. I want to solicit feedback from the community and always look for the next best analog. And I appreciate all your support today. I'll throw this back up there, and this kind of summarizes where we're going and what we've done so far. So thank you.
Thanks for the great talk. Our next speaker is Ian Andrews, and he'll be presenting about proglacial sediments and minerals in cold and wet Mars analog environments.
All righty. Thank you. Good morning, everyone. My name is Ian Andrews. I'm a current senior at Colgate University. And yeah, today I'll be talking about proglacial sediments and minerals in cold and wet Mars analog environments. This is what I'm using, right? Okay, cool. So for some context, we're going to be talking about eskers. And if you don't know what eskers are glacial fluvio sediment deposits that form as a byproduct of warm-based glaciation. And they form these like large kind of piles that you see. So on the left is an example of one in Iceland, and it's referred to as Troller Coaster. And has this it's just a huge kind of pile of rubble in a sense. And then to the right is an example of a satellite image of what an esker looks like. And that's from the Ring, which is an older esker site in Iceland. But I won't be talking about that specific one, at least later in this talk, but Troller Coaster will come back up. And kind of why are eskers even important? Like, why are we talking about that? Well, we're talking about eskers because we see these similar features on Mars's surface, and we're kind of curious as to whether or not these may be eskers or not. So the main objective of this project was really to identify if there's some kind of mineralogical signature to eskers on Earth in analog environments that could be used to potentially identify if these eskers or putative eskers on Mars can be identified from orbit or in situ using similar XRD devices with rovers. And then a second kind of goal of this project also was to see if there are any secondary mineral phases that are forming in this Mars analog environment that would give some kind of insight into the secondary minerals that we see forming on Mars' surface as well. So our actual field site is in Iceland, as I have said, and kind of zooming in because it's this very small portion, and then zooming in again, we get to our field site. And our field site, what we're going to be focusing on are three sites, those being emerging eskers, Troller Coaster, and this proglacial transect that was meant to get kind of an idea of the difference between, or trying to compare and contrast these proglacial sediments versus eskers, being that in order to identify eskers, we need to identify them differentiate them between the actual proglacial sediment surrounding it. So what I actually did in terms of working on these samples, I would start by sieving them down to less than 1 millimeter to get a bulk fine analysis of each sample. And then with that less than 1 millimeter grain size fraction, I would then powder it in a micronizing mill. And then I would spike it with 28% of corundum. And then after that, did XRD on each of those samples and used the Rietveld refinement in order to get some quantitative mineralogy and also some amorphous content information. So what did that actually look like? Well, for emerging eskers, which is the youngest esker site that we are currently studying, and for some more context as to what that actually looks like, that's what the esker looks like, and that kind of gives you an example of those facies as well, and kind of the general grain size idea. But in terms of the mineralogy, we see this CPX and plagioclase, which is good for Mars analog environment. We see quartz as well, which isn't as good, but as what has been said before, there's no perfect analog to Mars, but generally it does fit well for what we see. And then things like chlorite, we believe are just not forming in situ, but rather they are from a different parent rock and were likely transported to that location. And then a big thing that we see is this amorphous content across all samples, which we are going to kind of work on or talk about a little bit more for later in the talk. But it's also interesting considering that we see some similar kind of amorphous contents as well at Gale Crater using the ChemMin device. And then for our next site that we analyzed, we were looking at Troller Coaster and specifically looking at two different kind of facies of Troller Coaster, one being a more matrix supported, more fine grains and the other being more class supported. So that I'll just refer the matrix one being AB and class being AD. That's the easy way. So then for context, this is what we saw in terms of the mineralogy for both of those samples. So something that we're going to kind of dig into a little bit later, or is going to be a question later, is whether or not amorphous content is influenced by this grain size, being that we see for AB, which was the matrix supported, has this high amorphous content compared to the AD, which was that class supported site, which has a lot significantly less comparatively. And the only extra thing we also see in terms of mineralogy at this site is amphibole, which we're not sure why that was there and not in like the other esker site. But that's also something that we will look further into in the future. And then the last things that we were looking at were that proglacial transect. So that being the first samples being the youngest, and then as you go on, getting older. And this is just some more context as to what those like samples in that surface look like. So each site or each sample had a top and bottom layer. So it would be a surface sample and then also something at depth as well. And in terms of the actual mineralogy, we see that it's very similar to what we've seen before with the eskers, having that high CPX and plagioclase abundances, as well as this amorphous content that's spread across each and every sample. And when putting them all side by side, it really starts to look like they're all kind of the same. And though there's some differences between each of them, generally it's hard to actually distinguish something that could be called a mineralogical signature of eskers, just with this information alone. So from that, we are kind of concluding that, or not concluding, but at the moment it seems as though there is no mineralogical signature that can be used from this data to differentiate eskers from proglacial sediment, and therefore it would be hard to identify them on Mars using this sort of method. And then we also see that there are no crystalline secondary minerals forming in situ in these proglacial environments as well. And that's kind of giving us some insight into what may be actually going on Mars, where we don't think it's necessarily these cold and wet environments like in Iceland that are forming these secondary minerals. Rather, there might be some more warm conditions that are forming things like smectite and hematite on Mars. And in terms of moving forward, we hope to look further into that X-ray amorphous material, trying to seek out if there's any kind of glass or secondary mineraloids that are forming, and then also comparing that grain size information, being that what we saw for Troller Coaster had that kind of differentiation between more matrix and class supported and amorphous content. So digging a little bit deeper into that. And with that, I mean, I'm done, and thank you.
Thank you for the great talk and beautiful photos of Iceland. I'm jealous that you got to go there. Our next speaker is Riley McGlasson, and the talk is titled Detectability of Pore Filling Ice by Ground Penetrating Radar for Planetary ISRU at Hekla Volcano.
Thank you. Hi, everybody. My name is Riley McGlasson, and we're going to stay in Iceland for a little bit longer while I talk about some fieldwork that we conducted last summer, looking at the detectability of pore-filling ice using ground-penetrating radar. There's been evidence found for ice and regolith mixtures on both the Moon and Mars, whether it's direct or indirect evidence. Some of the examples of which I will show here. On the left, we have evidence of places in the Martian mid-latitudes that are consistent with subsurface ices, where darker blue indicates a higher likelihood of having subsurface ice present. And then on the right, we have a map from Hayton et al. In 2015, where blue in this case indicates locations in lunar PSRs, where UV albedos are consistent with regolith and ice mixtures as well. It's important to note that in the lunar case especially, we expect these concentrations of water ice to be really, really low, which could pose some detectability issues. Ground penetrating radar is sensitive to changes in the dielectric properties of the material you're looking at, which makes it really sensitive to looking for water ice, which is why we use it here. And we do already have radar sounding assets at both the moon and Mars, whether it's orbital or ground-based. However, understanding GPR data can sometimes prove ambiguous when trying to understand what unique composition of materials you're looking at, especially when the materials are dielectrically similar. Critically, in this case, water ice and a really porous regolith. So field testing, where we can ground truth what we're actually seeing in the radar data, can be really useful for trying to understand whether there's a diagnostic signature in this GPR data that we can use, especially when we're looking at low concentrations like we would expect on the moon especially. Iceland, as you may have seen in the past two talks, is a rich place to go and do planetary analog work. And the volcanoes in the interior of Iceland are rich mountain permafrost zones, which make them very well suited for looking for ground ice. So probably the most well studied in this context is the Askja volcano in the Northern Highlands. There's known massive ice buried beneath an accessible amount of tephra in the caldera of the volcano, as well as some pore filling ice too. The site that we look at instead is Hekla, which is in the southern part of Iceland. It hasn't been as well studied for its ice content. However, a study in 2007 by Kellerer-Perkelbauer et al. Mapped the permafrost depth across the volcano. This permafrost preservation was initiated in 2000 when tephra from an eruption buried it, and this permafrost was this preserved snowpack that is now densified is what Kellerer-Perkelbauer found in 2007, and what we are searching for, or were searching for last summer. However, Kellerer-Perkelbauer did not do any exploration into what type of ice was here, so that's something we're interested in looking at. So the main questions we're trying to answer here are what is the horizontal and vertical extent of buried ice at Hekla? How common is it? How extensive is this reservoir? And in what form is this ice preserved? Is it in massive ice like we see in this image from Shoemaker et al. In 2024, where we have buried ice at Askja, buried massive ice at Askja? And then also how good are we at identifying these signatures with ground penetrating radar? The main field methods that we used were common offset GPR surveys at 450 and 750 megahertz to better understand what's happening in the top 1 to 2 meters of the subsurface. We also conducted common midpoint GPR surveys at longer wavelengths to help us be able to more directly probe the subsurface velocities of reflectors that we're interested in. And then to ground truth our radargrams, we also dug a bunch of holes and conducted some trenching along our survey lines. Our two survey sites that we looked at last summer were at different elevations. The first was lower down at 760 meters in elevation. It is a valley in between two gently sloping peaks. On one side, on the left here, we have some lava flows that become exposed at the surface. And on the right, we have a meltwater channel that's actively eroding the surface and subsurface, both mechanically and thermally. Our second site was higher up in elevation. It is more protected from the prevailing winds than site one due to a low ridge along the edge. And this one consists of what we call the snow bowl, which is a dumbbell-shaped snow deposit. And then our survey grid was immediately adjacent to that, where we looked for ice in the subsurface. Even prior to conducting GPR surveys, we do have direct evidence that we are looking at some pore filling ice at both of these sites, or just regular ice and snowpack that's been preserved. So at both sites, we see dirt cones where we have ice and snow cores that are covered in millimeters to centimeters of tephra. And then in site one, we also see some tephra mounds with cracks in the top that are due to extensional stresses from buried snow and ice. And then at both sites in our trenching, we were able to pull up pieces of tephra that all have ice in between the pore spaces. I'm going to blitz through some of our radar observations here. So this is from site one. We see a reflector that indicates the transition from dry tephra to pore filling ice within the top 10 to 30 centimeters. And then between 1 to 2 meters, we also see a dipping reflector that we interpret to be the transition from this pore filling ice to a lava flow, which we believe the pore filling ice is overlying. And this is consistent with the geomorphological observations that where we see an exposed lava flow nearby, as well as some initial common midpoint survey results. Up higher, we see in our survey grid adjacent to the snow bowl about 10 to 20 centimeters of dry tephra overlying about 10 to 20 centimeters of pore filling ice. Our trenching was able to get to the bottom of this pore filling ice layer, and we find that in this case, it is overlying just more dry tephra. We also took a GPR survey across the snow bowl traverse and found that this snow deposit can be over 2 meters in depth in some places. We see some really nice internal reflectors within this snowpack, which we interpret to mean that this snow deposit preserves multiple seasons of seasonal snowpack. And then we also have a nice ice lens at the bottom where water has melted and percolated down and then refrozen in a nice flat layer at the bottom. So we are excited to go back to Hecla this coming season to explore the ground ice environment at different elevations, conduct new tests to understand the configuration of the ground ice, as well as get better, more quantitative data on exact concentrations of the water ice that we see. But from our surveys this past year, we find that while we do not find massive ice at depth as we do in Askia, we do find laterally extensive layers of pore filling ice at concentrations that may be analogous for lunar and Martian work. We think one of these differences may lie in that Askia in previous eruptions has blown its top, and there's a caldera at the top where massive ice can be well preserved, where Hecla does not have that. However, we were not able to reach the summit last year, so that's all just speculation at this point. But that's all I have for you today, and I thank you very much for listening.
Thank you. That was a great talk. We are a couple of minutes ahead, so we'll take a brief pause. All right, I think we'll get back on schedule now. Our next speaker, excuse me, is Alex Inneman, and the talk is titled "Examining Spatial and Temporal Variation of Methane Plumes at a Martian Analog Site in the Canadian Arctic."
Thanks. Yeah, so I'm Alex, and I'm going to be telling you about some work that we've done up in the Canadian Arctic recently. But first, I'm going to give some necessary methane background. So I was going to put together a slide, but Isa has very kindly made this lovely graphic talking all about what has been happening with methane on Mars. There have been a number of observations over the past couple of decades from Earth, from Mars orbit, and also in situ by the sample analysis of Mars tunable laser spectrometer on board MSL. It's SAM-TLS, if I say that again. And these observations have varied in magnitude. They varied spatially. It's unclear what's going on. Some of them have been contested to various amounts, and there has only been one time that a methane plume has been observed independently by two different instruments. So just to go a bit more into the SAM-TLS observations, there have been a number done over the almost 13 years now of the MSL mission, and they've shown both a seasonal cycle in methane and also with the couple more infrequent daytime measurements that SAM-TLS has taken, there also seems to be a diurnal cycle where we see methane during the nighttime and very little methane during the day. So there's clearly methane being put into the Martian atmosphere from somewhere and also potentially destroyed somehow. So what is needed is more methane observation. So SAM-TLS's methane enrichments are extremely resource intensive, so we don't get very many of them. So what I'm kind of interested in is how can future Mars missions better sample methane so we can understand what the heck is happening with it. So to that end, oops, that's the laser. To that end, we went up to the Canadian Arctic very, very far, about 80 degrees north to Umingmat Nunat, or Axel Heiberg Island. And this is up in the Arctic desert. It's a tundra permafrost region, and there is methane release from the permafrost. There's kind of a constant microseepage from the permafrost in this polygonal terrain. And then what we're interested in, there are also various methane sources, including these hypersaline cold springs. So what these are as the name suggests, very salty springs that have a fairly constant temperature, even when the air temperature is varying throughout the year. And there is also just, they act as a methane point source and release kind of these plumes of methane. So we examined two sites, the Gypsum Hill Springs and Wolf Spring. For the purposes of this talk, I will only be going through Wolf Spring. So in 2022, we went to Wolf Spring for the first time. The spring itself is in the middle of this kind of gypsum cone that you can see here. And it's tucked in down there. So we took a number of methane measurements using this instrument. This is just a commercial spectrometer. It's what's known as an OA-ICOS, which is off-axis integrated cavity enhanced output spectrometer. And what that means is basically there's a very small laser inside, bounces off a bunch of mirrors, and has a very large effective path length. So it can it has very good resolution in methane, and it also takes very frequent measurements. So when we sampled with it, we are sampling at a rate of 1 measurement every second. So at Wolf Spring, we sampled in 3 locations. We sampled at the spring itself, inside the cone, and then we sampled both upwind and downwind of the spring. And we wanted to get a sense for how methane varied along the wind path. And this is the data that we got there. So what you can see here is upwind of the spring, we see very little of the methane signal from the spring itself. So the average concentration that we see in there is actually very close to the background concentration of methane on the island up there. And then downwind, we're seeing a higher average concentration, and we're also seeing a lot of spikiness. And I will come back to the spikiness later. And then inside Wolf Spring itself, this was the data that made me go, wow, when I saw it, because we have these massive spikes up to like almost 35 parts per million. And in case you don't like graphs and you prefer numbers, this is it in number form. So again, basically background average concentration upwind, higher downwind, very high inside. And then you can also see this magnitude of the variation around the mean is highest at the spring itself. So the kind of sampling plan that we did in 2022, very basic, 3 measurements and completely in the direction of the wind. So we were kind of basically getting a one-dimensional idea of how methane varied around Wolf Spring. But we were interested in seeing more, getting more of a sense of how it varied. So if you imagine here, you have your point source, you have this methane plume kind of coming out in a fan from there. We want to know what happens when you move away into different parts of the plume or even away from the plume itself. So in 2024, another group took the instrument up again and got more of a 2-dimensional grid around Wolf Spring. You can see the points, how they're laid out over there on the right. The other important thing that we had in 2024 was an actual anemometer. So in 2022, I know that I said I went in the wind direction. The way that I determined the wind direction, if you're familiar with the Phoenix Telltale, it's very similar. I held up a piece of flagging tape and I watched the way that it blew. So having an anemometer in 2024 was great. This will become clear why in a moment. So we were able to take these measurements that we collected in 2024 and take the distance from the source and the wind direction, so that's that theta there, and get kind of a figure of merit out of that, and then plot both the average methane and the standard deviation, which is the proxy that we're using for the variation in the signal. And we saw how it fell off with increasing both distance and angle to the wind direction. So the relations that we plotted against these are up here, and you can see that there's a slightly better fit to the standard deviation. So from that, we kind of concluded that the variation in the signal may actually be a better indicator of proximity to the methane source itself than the absolute methane, the absolute concentration of methane. And this could be for a number of reasons, such as like methane coming in from elsewhere, which we observed at our other site, or other things like this. Very quickly, one other thing about the little spikes that we saw. So we saw these bubbles coming up of methane, and then the varying spikes. So we were interested in how often one might expect to see kind of releases of methane of various sizes. So we did plotted the power spectral density of this, and it has a relation of on the order of 1/f², which is Brownian noise. So that's what you see in Brownian motion, which is in diffusive processes. So that kind of makes sense, and we can kind of tell how often we'd be likely to see events of a certain magnitude. So what does this mean for future Martian missions? So we can kind of imagine like different mission scenarios. If we took, for example, an orbiter or something like this, it would likely not see the lower amounts of methane, which we're expecting to see more often. It's also not going to get that high frequency measurements. So we want to really be in situ on the ground, and we really want to be able to move around. So something like a rover, something even like a drone potentially, because then we can use the variation in the methane to localize the source potentially, which would be very interesting. And I see that I am almost out of time, so I'm going to wrap up there. Thank you.
Thank you for the excellent talk. I'd like to invite the 4 first speakers to come up to the stage, and we'll have 20 minutes of Q&A. There is a mic up on the chairs, and I invite anyone from the audience who has a question to come up to the mics to the front of the room. And again, introduce yourself, name and affiliation with your question. And if anyone is online, I'm not sure there is, we'll take questions from online as well.
Hello, I'm Reed Parsons from Fitchburg State University. My question is for Ian. I wanted to, first of all, say what a great method that you approached your project with by looking at mineral evidence for these processes, whereas the geomorphology can be, in some cases, ambiguous as to what's happening. I was interested if you looked at, say, grain size differences between the proglacial deposits versus the eskers, to see if there was a sorting effect happening in the esker as opposed to the proglacial deposits, which may be less well sorted, and that might be identifiable on Mars with thermal inertia differences between esker deposits versus non-esker deposits. So can you speak to that?
Yeah, good question. So I did do a lot of grain size analysis of all the samples. And it's hard to see if there's any kind of difference as well between the proglacial sediments versus the eskers that we see. But that isn't something that I like really looked into more. No, with that, if you mentioned what you mentioned about Mars. So with that context, that may be something I'd take another look back at. Could be really interesting. Yeah.
Hi, Joe Levy, Colgate University. A question for Alex about the methane. And just thinking about sort of differences between the Earth site and the Mars site in terms of the variability that you saw. How important is atmospheric thickness and turbulence to that big standard deviation? Should we expect kind of more dispersal of the plume on Mars or less? Or what do you think?
That's a very good question. I definitely the atmospheric situation is going to play a large role. I don't have a great sense for if we would expect more or less dispersal. But it would probably be something that would be like worth modeling and looking into. Yeah.
Sure, it's such cool data. Thank you.
Yeah, no worries.
Hey, Dan Lalich, Cornell University. I have a question for Riley. Two-part question. Oh, there's someone behind me, so I'll be quick. You had multiple frequencies out there. So first I was curious if like one of those was better than the others. And then also just generally from the holes and trenches, what's the contact like between the like overlying sediment and the pore ice underneath?
Yeah, thanks. So this was our sort of first crack at understanding Hecla. These are the first GPR surveys taken on the flanks, especially looking for this ice. So we didn't really know what to expect or what depths to expect these contacts to be at, which is why we sort of threw the whole kitchen sink at it. We found that the 450 and 750 megahertz were better for understanding what was happening at the top dry tephra to pore filling ice layer. However, we think we would prefer to go even higher in frequency to better understand what's happening there. The lower frequencies that we were able to do this common midpoint surveys with, they were not really able to resolve the top of the pore filling ice layer, but they were really useful for better understanding the geologic context. So they allowed us to get a permittivity estimate that was consistent with there being a lava flow underneath. So depends on what part we were looking at, but we'll be mostly taking higher frequencies next time.
And then the contact.
Yes, the contact. So trenching really helped us understand what the contacts were like. Up at site 2 in the higher elevation site, we saw sharper contacts. It was pretty evident. We were like scooping up sparkly bits of tephra that were sparkling with water ice in the sunshine, and it was pretty easy to see where that just stops and goes to dry tephra. We weren't able to dig through that pore filling ice layer in site 1. It was a little bit more cemented. We'll be bringing an auger next time. We just had a shovel, so it was a lot more difficult to dig through. But one question that I have is about that lower boundary as you start to lose that pore filling ice. Is it a sharp contact where it goes all the way to the lava flow, or is it so gradational that it goes to dry tephra in a way where the boundary is soft enough where we can't see it with the radar?
Hi, Eleni Ravanis, University of Hawaii at Manoa. My question is for Mike. Thanks for your talk. It's really interesting to hear all about the samples, and I think it's great that they're available to the community. I think you mentioned that you're going to be collecting samples in relation to the margin unit in the 2026 field campaign. And I was just wondering if you've decided upon the kind of locations that you'll be collecting them from, especially because we still have a lot of questions about the origin of the margin unit, and also if you have plans to collect analog samples for some of our Crater Rim samples soon.
Yeah, the plan is to collect analogs for everything. But we first prioritized the fan campaign because I thought that was the highest priority. I thought our igneous samples were pretty good, but compositionally, the sedimentary samples we had weren't great fits for kind of the more mafic provenance and time-sensitive stuff that we're trying to target. So that's why we prioritize that. And we have like the way we did it too is trying to be as thorough as possible. We created this analog rubric that's going to be available. We're going to have a publication on this, hopefully, to kind of really scrutinize our own samples that we're proposing to, or whatever's being recommended. And so there's going to be a whole chapter on just the sedimentary samples, and our plan is to turn to the margin unit, but we haven't even started that chapter yet, to be honest. So we're definitely going to need input from, people on the 2020 team who have looked at these a lot more than we have. Anybody who's done research in these type of areas too. So it's ongoing for sure. And then same with the outside of the margin unit to the Crater Rim, like you said. So stay tuned.
Thank you.
Hi, Liz Rampy, NASA JSC. Just want to say, happy to see a whole session on analogs. That's awesome. And especially awesome to see early career folks giving these great talks on it. So thank you very much. My question is for Riley about your analog site at Hecla and this ground ice, thinking about the moon. So, lunar ice is likely not just H2O, but NH3 and CO2 and other things. So I'm wondering, one, if you've looked at like the ice at your analog site and its composition, its purity, or how these impurities can affect, radar observations of ices.
Yeah. So we didn't bring any like geochemical tools. We were just looking from a geophysical standpoint. So as long as you have any material changes that affect how wave speed propagates through a material, you can get a sharp reflector. So whatever type of ice that is, we know just based on the conditions that we have, that's going to be primarily water ice or exclusively water ice, but water ice is highly conductive, which makes it really sensitive to radar. So it'd be interesting, but we just didn't have the tools to look at that.
Okay, so unlikely that these small impurities of other ices in like lunar water ice would affect the radar observations?
I think that's something that we would need to do more lab experiments on.
Cool, thanks, Riley.
Mm-hmm.
Hi, S.J. Ralston, they, them, Momentum at Johnson Space Center. I have two questions, if that's okay. Okay, the first one is for Ian. Great talk and a really cool field site. I wondered, did you notice any patterns in the distribution of amorphous material was it spatially correlated in any way that you noticed?
I would say I didn't see anything spatially about the amorphous content that was really like that I could really notice. But yeah, something about grain size is something we're trying to get at. There were some samples, even for the Esker sites, that would have a higher percentage of that fine, like smaller grain sizes, and they would have this higher amorphous content. But it wasn't. But that's something I need to look into more to really identify that, or if there is some kind of spatial distribution of amorphous content. Yeah.
Okay, cool. Thank you. And then my second question is for Alex. Also a really cool field site. My question is about that gypsum cone, which I kind of am not quite clear on what the scale of that thing is, but it looked pretty big. Do you think methane trapped in it somewhere that we would be able to find?
That's a very good question. I would suspect so. It's pretty porous just from my memory. And we definitely found like within the cone itself, there was just like a lot of methane hanging out in there, like in the opening. of it. So I would suspect that there's some like in the structure of it itself, but I'm not entirely sure.
Cool, thank you.
No worries.
We still have about 9.5 minutes for questions, and I do want to welcome our attendees that are online. And if they have any questions, to put questions into the chat. And I believe my co-chair might have a question or two.
Pages of questions. Yeah. Go ahead, I'll start. I have a question for Ian, like a clarification and then a question. The clarification is about the difference in amorphous composition you saw between the matrix and the class supported. When you were doing your XRD analysis, were you looking at the same grain size separates for both of those? And in that grain size separate, you still found less amorphous in the class supported?
Yeah. So I didn't actually work on those specific samples.
Okay.
But I would imagine, I believe from what I've been told that those samples were done like bulk, like it wasn't like it was powdered with like it wasn't sieved down to less than 1 millimeter. I don't know if
I have information on this.
Okay, yes.
It was the less than 1 millimeter size fraction for both.
Okay, so it wasn't like you had more fine grained in the matrix supported, and that was the carrier of the amorphous. It was evenly distributed. Super interesting. Yeah, and then my question is about the conclusion about the lack of crystalline secondary minerals and the requirement for warmth. And I'm wondering if time is also a variable. And so the question is, how young or old were the sediments? And is there a chance maybe if they stuck around for longer, you might have some crystalline material forming?
Yeah, so that's interesting because yeah, the sites that we mainly looked at were like younger esker sites, and emerging eskers being like one of the youngest currently. So if we looked at a site like the Ring, which I showed in that first image, which is a much significantly older site, there could be other things that we'd see in terms of secondary minerals forming, potentially from aqueous alteration and different kind of things going on there. But yeah, without that information yet, I can't confirm or deny, but yeah.
Cool, thank you.
We have an online question. So this is from Bumsu Kim, and they say, Q to Mike. I saw Sherlock's team findings on poppy seeds early this Wednesday. Where would you guide me to find such a site or sample on Earth?
Yeah, those were super cool samples. Good question. Haven't thought about it too much until sitting in all those talks, but I know Adrian Brose was saying that some red beds on Earth might have some of those, at least the green spots. I don't know about the poppy seeds and the leopard spots, but perhaps some red beds on Earth. So I'll be looking into it. Good question.
I also have a question for you. I'm wondering how much context information is provided with the samples when someone requests one?
Yeah, so all the field notes are they're pretty detailed field reports that the team was required to do, and including pictures and everything from what a geologist would do in the field, from using a hand lens to identify olivine grains in the regolith. So that's all going to be available to the community. I know the rock sample team is also working on kind of compiling all that into a publication too. So hopefully everything that you need is available. And I think the field team names and everybody are there too. So if you ever need to reach out for something you missed, I'm sure they would be happy to answer some questions.
Okay, so I actually have two questions. The first one is for Mike. I'm wondering if can the requested ASL samples be modified in the lab? Or would we purchase the samples, or is it like a renting situation?
No, I think it's like they're yours. The point is to kind of hone in on your techniques if you have them in the lab too. Now, these are going to be the most precious samples we ever have, probably period, when the MSL samples come back, MSR. And so, hone in on those techniques now, understand how things that are time sensitive, sterilization sensitive might change from your techniques, come up with an architecture of how you might handle the sample when it gets into your lab. I think that's part of the process.
Cool, thank you. And my second question is for Riley. I'm not super familiar with Martian geology, but I'm curious, how common do we think the tephra ice layering that you were studying, do we think that's common on Mars?
Well, so the swim team has done a lot of really interesting work. That's where that Morgan et al. 2021 figure was from. They've done a lot of interesting work at using combined techniques of GPR, geomorphology. I think they had like 5 total methods to try to identify places in the mid latitudes where this is where we have subsurface ice. So what exact form that is in, I think remains to be seen. But like at the Phoenix Landing site, we were able to see direct evidence of ice and regolith mixtures. Even at the poles where we have massive ice, you still have a lot of dust content that's mixed into the ice. So we do see this ice and regolith interaction all over, whether we have massive ice or ground ice on Mars, and then mostly ground ice on the moon.
Cool. But so tephra is like super porous and dense, and unconsolidated. And I'm wondering if we believe there to be like, is there tephra on Mars?
Yeah, so this I believe is a better lunar analog. But thinking about ground ice and radar observations is broadly applicable to other rocky and icy bodies. But I think this site is a better lunar analog.
Cool, thank you.
Got about 3 minutes if anyone else has a question or a comment for speakers.
Yeah, I'll ask one more question of Mike about that last sample site you talked about, the last analog site, the one in Italy. Can you tell me more about it? It's a conglomerate.
Yeah, it's a really complex geological history that I haven't even figured out completely yet. I came across it just kind of Googling basaltic conglomerates or mafic conglomerates, and that came up, and it was an article published in 2022 by Luca Borelli, and I've been reaching out to him and talking to him about him. So what it is like an ophiolite that was uplifted and then reworked and then cemented into a pebble supported conglomerate that like the matrix is clay rich and has smectite. I was hoping somebody would ask me about my XRD patterns. But it had smectite and it had serpentine in there and just like ultra mafic provenance. So just super cool. That's not really been studied that much. So yeah.
All right, I'll do another one. So again, for Riley, you mentioned at your site, and you could see in the radar images that this is like pretty like laterally widespread. My question is like, how laterally widespread? Like, is this something where like if you went up and looked at 5 areas, all of them would have this ground ice signature, or would you go to a couple of them and just not see anything?
Yeah, so there was one additional site that I didn't have time to show that we used sort of as a control site that was nearby our second site. So at higher elevations where we might expect ice to be more stable. However, this unlike the site that I showed that was at higher elevation, lacked that small ridge of wind protection. So it was really, really exposed like a saddle on the mountain. And we ran a survey there and we didn't see any ground ice. So we saw ground ice at 2 out of the 3 locations. And we think a lot of this is controlled by how protected the environment is, whether by deeper tephra cover or from the wind.
Thanks. That'll need to be our last question. Thank you so much for your great talks. All right, so we've got about 30 seconds before we can get started on schedule. All right, well, our next speaker is Joseph Levy. That's a very long title, so I'll read the first part of it. Drone-borne measurements of time-resolved changes in a shallow groundwater plume.
All right. Well, thank you everyone for being here. I'm happy to share some work done alongside Abby Freeman and Flannery Hogan, who are here today. Here's the big problem is that everything good on Mars is in really steep places. And that makes those good things inaccessible. It's hard to rove to them. It's hard to sample them without falling down the hill. And so as a result, we rely on remote sensing. But when we rely on remote sensing, we actually are limited by the detectability of things that are of interest to us, like these recurring slope lineae in Newton Crater or Capriati's Chasma. The time of day that we're locked into with orbital spacecraft changes the detectability of things like water, which may be involved in the formation of a variety of Martian landforms. And this really matters because soil moisture-based landforms on Earth change over very rapid timescales. So we're looking at a time-lapse set of images here from Garwood Valley and McMurdo Dry Valleys of Antarctica, looking at some salt patches that are on the wall of these gullies, and their albedo changes rapidly as a function of time of day, largely as a function of solar position. So if the sun is shining on them, they're warm, they deliquesce. When they're in shade, the relative humidity jumps up, they become wet. They effloresce when it's low relative humidity, and they deliquesce when it's high. So really, relative humidity is driving changes over minutes to hours, and we have to be there to see it. So this is where the HeliHabitable project comes in. This is Abby's brainchild, and I am a supporting player in. And our goal is to advance helicopter operations and science for steep environments on Mars, like Valles Marineris. Think Martian helicopters, but bigger and with even more instrumentation. And the science goal here is to determine how time of day affects the spectroscopic detectability of water in highly evaporative environments. So if aqueous processes are active on modern Mars, can we actually see them depending on when we go? So since we couldn't go to Mars, it's a little bit expensive and tickets are hard to find, we went to the Alvord Desert in far southeastern Oregon. We're outside of the little town of Fields, and we're looking at this large geothermal groundwater plume that comes out of the Steens Mountains. So this is the Alvord Hot Spring Discharge. It flows out of the mountains onto the Alvord Desert Playa, which is a wilderness study area on Bureau of Land Management land. We happened to arrive there when it was about as Mars-like as it gets. This was wildfire smoke from last summer. So we got a lot of ambiance. And this is a drone's eye view. So we took a series of air photos while we were there, plus a bunch of other more interesting sensors. The little chevron down in the bottom of the map there shows the view from that last ground-based view. And what we were doing was trying to map discharge in the Alvord Desert, in the Alvord Hot Springs plume, as a function of time of day. So we were there in late July and early August, the hot part of the year. We wanted to understand time of day observations, so we started early in the morning and worked until about noon when the dust devils would have knocked the drone out of the sky. And we took a series of measurements, including near-infrared spectroscopy and microwave emission remote sensing, complemented by some ground-based time domain reflectometry sensors. So we're going to zoom in on the study site down here, and what we're really trying to do is detect the 1.4 micron absorption from water. So we want to know if water is present, how detectable is it? What we want to do, pardon me, is measure down at the base, come on, go back, you can do it, of this 1.4 micron absorption. We want to measure here, there's not enough photons in the sky. Even in the Eastern Oregon desert, there's too much atmospheric water vapor, it gobbles up those photons. But when we measure at the edge of the 1.4 micron water absorption, around 1500 nanometers, we can see that standing water has almost total absorption of photons at that wavelength. Sort of damp soil in the green has some absorption, and dry soil reflects almost all of that light at 1.5 microns. So we've been really successful in the past at measuring this 1.5 micron sort of edge of the 1.4 micron absorption. So what we do is we fit a continuum across our spectra of damp soils, measure the band depth at 1.5 microns, and then we normalize it to the brightness at 1.5 on the continuum to try and get a measure of this continuum removed water index sort of query parameter. So we know from lab measurements that this is very sensitive to the total gravimetric water content or the lab-based water content of the soil. And so if we see this, we should be able to know there's water there. So what did we see? Well, looking at the Alvord Desert plume here, you can see that the plume is advancing, kind of like a recurring slope lineae on Mars. Just for fun, it advances about 10 to the minus 4 meters per second, which is about 10 times faster than the fastest RSL on Mars. But the important thing is that hot spring discharge albedo is dynamic over time. You can really see it changing. What do the spectra show? So we'll kind of zoom in on this study site here, the sort of highlight of the plume. And I want to show you first some remote sensing data and then some data from our sensors that cross the plume and go down into it. The thing that I'd like you to see is first the query results, so the spectroscopy results. I'm going to show you a series of images of basically absorption depth, this query parameter. So here's our first drone hyperspectral cube looking across the hot spring. So anywhere where query is red or 0 values, basically we have no band depth, we have no absorption from water. 1 is the entire spectral response at 1.5 microns is in the absorption feature, so that is standing water. And so you should see we do a great job of capturing in the blue the wet part of this plume and then edging into the greens slightly drier and drier soil. What does it look like when we see this as a time-resolved process? So this was our 917 flight. A few minutes later, we changed the batteries on the drone, flew again, and you can see now our 1006 data overlaid on the 917. And again, we're capturing this wet-dry transition. But importantly, what I'd like you to see is that in areas where we had dark blues before, now we have greens. Let's see if I can step back, living dangerously. So we have dark blues, lots of water, and then even 30 minutes later, we're moving into blues and greens. We're seeing less of this spectral absorption. What does the microwave radiometer measure? Well, this is measuring emission of microwave from the surface. Water absorbs those microwaves, and so it allows us to measure moisture content in the upper 5 to 10 centimeters instead of the upper micron of the soil. So I'll show you some microwave radiometer, very preliminary results, where blue is lots of water, nearly 100%, edging in 10% bins down to the red where it's totally dry. And what you should see is that the Alvord Desert, in fact, has some water in it in this plume. So to recap our science goals, can we detect plume water in this RSL analog site? And the answer is yes. We can use a helicopter. We can do it. There's a geophysical signal consistent with water. How does time of day affect the spectroscopy? And we see some preliminary evidence of drying. But now I want to show you something really surprising. And that is what happens when we actually look at what the sensors are seeing versus what the remote sensing is seeing. So we'll zoom in on our sensors here. And the first plot I want to show you is temperature on the y-axis and time of day on the x-axis. All these gray lines are our drone flights. It gets up to around 40 degrees Celsius on the ground. The peak temperature was 108 Fahrenheit on the playa. It was a hot place for field work. But what you should see is over the course of the day, of course, in the desert, it gets warmer and warmer and warmer during the course of our observations. Now, when you look at the soil moisture measurements coming off of our ground-based probes, you should see now volumetric water content over time for a series of sensors going across the plume. And what we're really seeing here is that soil moisture is broadly flat or slightly increasing over the measurement window. Now, these TDR probes have 9.4 centimeter waveguides, so they're about the size of your finger, and they're poking into the ground, measuring soil moisture in an integrated volume. Now, the spectra, on the other hand, this continuum-based water index query is now plotted here on the y-axis. Now plotted here on the y-axis over time. And what you should see is that our band depth associated with the 1.4 micron water feature decreases over time. It gets less and less and less and less. So by noon, even the wettest parts of the plume are almost devoid of water, according to the remote sensing. Here, if we plot this up for all of our sensors, that blue one was the query value at our wettest sensor. This is now at all of the sensors. You should see this general decrease in the detectability of water with the 1.4 micron feature over time. On the edges of the plume, there's kind of like a wetting and then a drying. But even in our really wet areas here in the blues and the grays, we're seeing less and less detectability of water with time. So by noon, all of these values are less than 0.1. They're basically approaching background for dry soils. So where does that leave us? It leaves us here. This is a beautiful time lapse that Abby took of the field site showing the plume advancing. This is in time lapse. Remember, it's 10 to the minus 4 meters per second. This is its average advance rate. You can see the drone flying overhead as we mow the lawn with our spectrometer and radiometer. But the important thing here is that if we are locked into if we're locked into afternoon observations of this plume, we would miss the water. Even though the soil is visibly wet, it is visibly dark. According to the spectrometer, it is completely dry. So there is a mismatch going on between the hydrology at this site, what's going on in the surface and the subsurface, and what we can detect with remote sensing, and hopefully a future Mars helicopter that can sample early in the mornings or later in the evenings would help resolve this uncertainty. So with 14 seconds to go, thanks so much. Talk to you all later.
Excellent, thank you. Our next speaker is Taylor Plattner. And the title of the talk is Evidence for Acidic Bleaching and Dominant Groundwater Processes in End-Member Hypersaline and Acidic Lakes in Western Australia.
Right, thank you for the introduction. I'll be taking us down under to Australia today, so I hope you're okay with that. Like the introduction, my name's Taylor, and I'm going to be talking about the OAST team fieldwork that we've done in collaboration with the Esperance Dalarak Native Title Aboriginal Corporation in Western Australia. Okay, so where did we do this fieldwork? This is just the Ilgorn Craton in Western Australia, which is where we sampled by these stars on this map. And basically what's really cool about the Ilgorn Craton is that there's like thousands of ephemeral lakes across the whole surface, and they're mainly concentrated in these Paleo Valley channels or these catchments indicated by these weird branched colored features on the map. And what's really interesting is if you look in the literature, you'll see that most of the literature has done a lot of work on the groundwaters in Western Australia, and that they've seen regional trends with acidity, salinity, and oxidation potential across catchments in the Ilgorn Craton. However, like I said, there's thousands of these lakes, but they haven't been extensively studied in terms of lake water. And so that's kind of what we're going to focus on today. And in the literature, they've only really been described as having a random distribution of pH. And so it's currently unknown whether there are trends in lake water geochemistry across catchments. And I'm specifically going to be talking about one trend that we see today geochemically, and then some end members geologically that we see, and then implications for Mars. And this is just a color map kind of showing this groundwater acidity between catchments. Okay, so what's really cool about these lakes is that they go through these wet-dry cycles through time. And so it's kind of key to sample both of these seasons. And in this wet season, as you can see, it's thought to be dominated by rainfall and runoff. And then you slowly evaporate out your water and you start to precipitate out salts. And then this dry season is really indicated by like most of your evaporated water is gone and you're left with these salt pans. And so it's really key to sample both seasons to really understand preservation and habitability through time. And it's thought that in this dry season, there's a large contribution from groundwater flow into these lakes, which we have direct evidence for, which I don't think I have time to actually show the video today, but just know that this whole cycling is constantly happening through time. Okay, so just so you see, these are just our methods. It's pretty self-explanatory, showing you what probes that we used in the field. So this is some pictures of the OAST team looking, sampling some boreholes, lake water, and also the geology surrounding the lakes. And we mainly did a lot of in situ probes for pH and salinity, which I will be talking about today. And then TDS, we also did in the lab, so measuring like total dissolved solids from the samples. And then last intro thing, I promise, but to understand what I'm going to mention in the next couple of slides, you have to know what's going on in the subsurface. So there is a difference between shallow groundwaters and groundwaters at depth, and it's due to these acidification processes in the subsurface in Western Australia. And so it's thought that these two processes are called like pyrolysis and the oxidation of sulfides, such as pyrite. And this is just a schematic showing kind of what happens around groundwater evolution around sulfides. So these conditions do vary with depth. So if you're at groundwater at depth, so you sampled with some boreholes, it's thought that these groundwaters are more highly reducing and more near neutral. However, when you get to the top of the regolith profile, this is when pyrolysis is thought to dominate and really take control in this like Vadis zone, which is above the water table. So it's thought that these shallow groundwaters are going to be more acidic than groundwaters at depth. So just keep that in mind. And then we also have a pH limit in groundwater at depth. And so this is like a pH limit of 3 due to buffering by aluminosilicates. And so it's thought that if you see aluminum, silica, iron, sulfate in your lake waters, that is evidence for some groundwater input, which we do see with these lakes that I'm going to be talking about today. So these are the two catchments that I'm going to mention because they're the most extreme geochemically. So these are the catchments, Cam Paleo Valley Channel in the blue, which is near Hayden, Western Australia, and then Salmon Gums, Western Australia. There's a bunch of lakes over there in the Cowan Paleo Valley Channel. And so those two lakes have the most saline lake waters and the most acidic lake waters. And we'll kind of talk about that. So remember when I said groundwater at depth? So what I'm highlighting in red here is these diamonds are groundwaters at depth in the Cam Paleo Valley channel. So remember it was blue. These next two plots are just these two Paleo Valley channels. And so this is pH versus salinity. And what we see in the Cam Paleo Valley channel is more near neutral pH water in the groundwater. But we do see like less saline than seawater, which is indicated by this dashed blue line. And then if we look at lake waters, it's quite different. So we see that these subsurface interactions really play a role here, and that from wet to dry, which just so you know, the outlines are the study that's done. So I know there's a lot of colors, but our data is in the wet season, it's outlined in blue. In lake waters are the circles, and then the outlines in yellow are the dry season. So we see a drop in pH and an increase in salinity, which is consistent with the literature. But what you see is this groundwater pH limit of 3, and the only things to really get below this pH limit is lake waters and then shallow groundwaters, which are indicated by the triangles, and there's only one here. And then there's more data for this Cowan Paleo Valley channel, and it's basically the same kind of trend that you see, except the only difference here is groundwater at depth is more acidic. So this is like what's circled here, showing that these groundwaters are a little bit more acidic and a little bit more saline than seawater. And then we see the same trend with lake waters where we see a drop in pH and an increase in salinity. And so what does it mean for these two catchments? So these are, again, the most extreme geochemically, but we also see other trends that are pretty extreme in terms of water activity and dissolved oxygen. But we also see the highest concentrations of aluminum, iron, silica, and sulfate. And so the trend that was mentioning today is that these are really a combination of groundwater, rainwater, and subsurface interactions to produce the lake water geochemistry seen. And so this is basically just saying that lake water is more acidic than groundwater, which disagrees with the literature in which they find that groundwaters are more saline and more acidic. And we do see that in other catchments. So it does depend on where you are in the catchment with what your lake water and your groundwater at depth and shallow groundwaters are actually like. I'm going to skip this just for the sake of time. And I'm going to just mention this briefly, is that there are really coolest lake is Lake Gunter, which is in the Cam Paleo Valley channel. And this is just a picture showing like wet to dry, and then some of these geochemical parameters from wet to dry season. So it's quite extreme. It's like the most saline, most acidic lake. And what's crazy about this lake is out of all shallow groundwaters, groundwaters at depth, and lake waters, everything is sodium chloride brine except Lake Gunter. So it changed from wet to dry season. Feel free to ask me about this in the Q&A because I can talk more then. But the two types of geologic end members that we see in these environments are these two seen here. So this is end member type A, which are mainly these most common across Western Australia. So to me, they're quite boring because they don't have a lot of stuff going on geologically. So it's just really a salt pan and aluminum clays in association. Whereas these lake environments, which are only about 5, these are end member type B, and they're really more exposures of the regolith, and they're more truncated profiles showing these outcrops of rock that are really recording a history of what's going on in these environments. And so these are dominated by clay minerals, quartz veins, and iron oxides such as goethite, hematite, and jarosite. And so we also see layering of clays in these environments, and we see like cements of iron oxides, and then evidence for acidic bleaching, which I don't have time to talk about, but I can talk more. I can't show this, even though it's the coolest video I've ever seen. But the analogs that we kind of think these are relevant for on Mars are more acidic lakes. And these are typically like on Mars, the Terra Cernum region. So we're thinking this because these areas also host clays in association with the chlorides, and they're also thought to be found in like belly networks. And we also see evidence for secondary mineral assemblages that are very similar to what we see in Western Australia, and evidence for higher water to rock ratios in these areas. And then I'll just wrap this up and say that this, I've talked about these extreme end members here with like insane geochemistry going on, but we do still see microbial life in these environments. So regardless of these geochemistry conditions, we see this. And regardless of pH or salinity, this is all really recorded in the salts. So they are trapped in the salts through time in these environments, regardless of pH or salinity, which has implications for future missions to Mars. And I will just leave these conclusions up here and just say that we are wrapping this up in a paper to be submitted soon. Thank you.
All right, thank you very much. We're going to stay salty with our next speaker. It'll be Emmy Hughes talking about climate-dependent salt formation and hypersaline Canadian lakes as analogs for Hesperian Mars.
Awesome. Thank you so much. Hi, everyone. I'm Emmy Hughes. I'm a PhD candidate at the Georgia Institute of Technology. And today I'm really excited to talk to you about these really fascinating lakes that we've been looking at in British Columbia, Canada, as analogs for Hesperian Mars, as it says in the title. So I think many folks in this room think a lot about the early Mars climate, but just to kind of contextualize this, the early climate of Mars is relatively unknown in terms of whether it was cold and wet or warm and wet or cold and dry. And also, of course, maybe even more likely a combination of these states over time. And because we don't have active surface hydrology now, at least in terms of running water on the surface, our way of kind of investigating these ancient processes is through the mineralogy that is preserved on the surface from Mars's past, which does record information about the environments in which these minerals formed, including things like pH and alkalinity. Something that I'm really interested in is using minerals as climate indicators or temperature indicators. So, how do we think about their hydration states and assemblages as a proxy for climate? So something like cold and wet versus warm and wet versus cold and dry. And so I'm thinking about this in the context also of lakes on Earth. So there's a series of lakes in British Columbia, Canada, called the Basque Lakes. These are very relevant to Hesperian Mars. They're enriched in magnesium, sodium, sulfur, as well as chlorine and some additional cations. And what's really particularly interesting about these lakes is they provide two end members of freezing and evaporating concentration mechanisms. So in the winter, these lakes freeze over and you have cryoconcentrated brines with a different set of minerals than in the summertime when through the fall, they will evaporate to completion. So they really do kind of give you that cold and wet and warm and wet, relatively, end member environments. So our major questions here are, what are the mineralogical and geochemical indicators of a colder and icier climate? We can look at that in situ. How quickly do minerals respond to climate forcings? So do we see annual changes, or is there some more preservation potential? How accurately are our thermodynamic models predicting these mineral assemblages? So that's really a kinetics question. And then what are our best techniques for distinguishing these materials based on season? So, what would be most useful to use on Mars for that? And I'm actually going to give my takeaways first so that you can hold these in your mind as we go through a series of plots. So we've had 6 field seasons. 3 of them have been in the fall at the end of the evaporative period, and then 3 in the winter. What we've seen is that in these high magnesium hypersaline lakes, we see either some structural incorporation or some adsorption of magnesium into gypsum that's precipitating kind of around the edges of the lakes. We also do see major seasonal changes, and these are really primarily linked to hydration state and also variability of gypsum abundance. There appears to be some kinetic inhibition of some of these kind of lower hydration state magnesium sulfates that are predicted based on the relative humidity and temperature data. And then gypsum is really Raman active. I'm curious if others have encountered this. We're seeing really sort of strong gypsum peaks, even at very low calcium weight percents. So orienting us with the thermodynamic data, if we use FreezeChem to model a Basque Lake composition via freezing and via evaporation, we get 2 different sets of minerals. So via freezing, you see this highly hydrated magnesium sulfate, meridianite, which is named for Meridiani and was identified actually first in the Basque Lakes on Earth, and also mirabolite, sodium sulfate tin hydrate. In evaporating scenario, you see things like epsomite and bloodite, warmer temperature salts. If we look at the relative humidity and temperature data from in situ collected in the field in comparison to this stability field, we see that we should be seeing epsomite, mirabolite, and meridianite in the winter. Meridianite specifically in the winter brine, where we have a water activity and temperature consistent with the meridianite stable field. And then if we're looking in the fall data, we have hexahydrite, starkeyite, kieserite kind of stable or metastable. So here are our sampling locations from the lakes. And for the rest of this talk, the diamonds will represent winter data, pools, crusts, and muds, and then the circles will represent fall data. Okay, so here we're looking at in situ XR X-ray fluorescence data from the field, and it's plotted again as diamonds for winter and as circles for fall. So what I want to draw your attention to is we see sort of a variation in the ratios of magnesium and sulfur, the relative amounts of these, depending on seasons. So in winter, they're kind of proportionally lower, proportionally higher in the fall, but they all fall along this magnesium sulfate mixing line. This is probably due to the higher hydration state of these winter minerals. So you can see that kind of shift there. The other thing is that we do see gypsum, but only a few points are really falling clearly along this calcium sulfate mixing line. A lot of materials with high calcium also have excess sulfur. If we look at this in relation to the Raman peaks that are associated with the sulfate anion intensity, vibrational peak, what we see is that, again, a lot of these materials, and this is just plotting fall data, a lot of these materials have peaks consistent with hexahydrite or epsomite, or maybe slightly, hydrated epsomite from the fall. So these kind of lower hydrated magnesium sulfates. We also see consistent Raman peaks with gypsum at 1,008 inverse centimeters, but those two still fall along this magnesium and sulfate mixing line. So you'll see in these kind of blue circles, we're plotting gypsum peaked materials in the Raman that has this high magnesium as well. And then same with our calcium sulfate diagram. So you can see a lot of materials at low calcium, relatively weight percent contributions. You'll still be able to see this high gypsum peak. And then you'll also see these kind of double peaks with magnesium sulfate peaks. So that's what some of these materials looks like. It's often kind of efflorescing up the muds. If we look at the winter Raman data, we start to see much higher hydrated peaks associated with the Raman data. So we start seeing this 988 Raman peak plotted in the pink diamond. So you see there's quite a few of those that we do not see at all in the fall data. And then we also were able to identify meridian. Oh, I'm going to go back one. Maybe not. Yeah, okay. We also were able to identify meridianite from this 990 peak in the winter as well. Meridianite came from this core, so exactly where we predicted it in the brines where they're cryoconcentrating. Meridianite does seem to form through that process, which we're able to see here. And then at the kind of crusts that are forming along the edges of these lakes, we see this 988 vibrating peak in the Raman that appears to be sort of metastable. And if you remember from the humidity data, in the air temperature, epsomite maybe should be the stable phase. So it's interesting that we're seeing something that looks to be a little bit of a mixed hydration state. So our key takeaways here then are that we have these high magnesium bearing gypsum crusts that are forming in these pools. And I think this indicates, in these high magnesium sulfate bearing systems, if you're preserving this in the rock record, and gypsum being more stable may have a little bit of a higher preservation potential. If you see high magnesium, structurally, potentially in these materials, it may indicate a magnesium sulfate rich lake for formation. We do see major seasonal changes. This mainly includes, the sort of variable hydration state for the magnesium sulfates. And also we see some real loss of gypsum in the winter. So the data collected in the winter time has fairly low gypsum abundance, even though it's also still Raman active. So there's some, potential that we may be able to see seasonal cycling on Mars. For that reason, we do see some kinetic inhibition of hexahydrite and kieserite. So these, again, were stable based on the relative humidity and temperature data. They weren't modeled in the thermodynamic models, and we didn't really see any kieserite, likely due to just, the high water content at the lakes. And then finally, gypsum is highly Raman active, so it may be over predicted by a bit in Mars data. So, we may be able to see it much more easily in mixed salt assemblages. I have a little extra time, so I'm just going to go to a quick backup slide here too. So one other thing that we're working on is using visible near infrared data and developing band parameters for these data as kind of a proxy for what we would do with CRISM data. So we're able to sort of develop these quick band math calculations and then plot them in this space. And you can see seasonal variability via this technique as well, where you see more gypsum-rich sort of plotted material in the fall, more mirabilite in the winter, et cetera. So this is another way of kind of revealing information about these systems relative to Mars. So I think I'll end it there, but I just want to say I am graduating soon and looking for postdocs. So if anyone wants to chat, very happy to do so. And I'll just go back quickly to the conclusion slide. So thanks very much.
Thank you. Our final speaker in this group will be Zhang et al. Talking about solute provenance and hydrological evolution in the Miocene Reef Impact Crater Lake as recorded by strontian isotopes and implications for Mars.
Thank you. For numerous paleo lake basins on Mars, to date, it is unclear how it is unclear about the history of their inflow pathways, how the lake size and volume change over time, and the lake and the basin evolution of those impact crater lakes. In impact crater lakes, both groundwater and runoff could interact with the local bedrocks, leaching calcium and magnesium from them, which then would accumulate in the lake and precipitate as carbonates. These carbonates contain important information about the hydrological history. When calcium carbonate precipitated, another element called strontium can substitute calcium due to their similar geochemical behavior. Therefore, strontium isotope helps to identify inflow sources, since older rocks have higher 87 to 86 strontium due to longer radiometric decay. Without any chemical details, the short rationale here is different bedrocks can produce different 87 to 86 strontium during weathering processes in their natural waters and in the precipitated carbonates. The studied Reef crater is a 26-kilometer wide complex crater in Germany. It has an inner ring structure that comprises of former collapsed peak material, and at the crater margin, it has a terraced zone. In the field, two impactite formations were preserved. That is the melt-bearing breccia known as the Suevite and the continuous ejecta blanket known as the Bonte breccia. What is unique at Reef is it has a complicated and diverse stratigraphy in its pre-impact target rocks. Later, we'll use this stratigraphy to reconstruct impactite. After the impact, a paleo lake basin formed and accumulated thick carbonate-rich deposits in the central crater, as shown here, and these carbonates would be ideal for measurement of strontium isotopes. And the result of the strontium isotope is shown by this curve here, ranging from 0.7104 to 0.7140. Note that a difference of 0.001 would be considered significant when interpreting their provenance. We mentioned that the 87 to 86 strontium of carbonates is sensitive to change in inflow lake waters and weathering end members. In our Reef crater lake, the inflow waters, they leached and eroded the impactite formations, which is our Suevite and the Bonte breccia. While we could measure the strontium isotope of the Suevite, which is marked by the red line here to be 0.7125, it is almost impossible to directly measure the strontium isotope of the Bonte breccia because it is too heterogeneous. we then designed an experiment to simulate ancient weathering solutions derived from the Bonte breccia. On the left side are the pre-impact target rocks. We sampled all these rocks and used water to leach them, then measure the strontium isotope ratios from these leachates. We know the excavation depth and the thickness of this stratigraphy. We then calculate the relative volume and mass fraction of each each sedimentary formations to constitute the Bonte breccia. We then proportionally mixed these solutions according to the ratios we derived from here. And this mixture solution would represent a homogeneous weathering solution that is derived from the Bonte breccia. And the result is set to be 0.7101. So the result of the Bonte breccia strontium isotope result is shown by this blue line here, and it almost perfectly explains the lower range of the 87 to 86 strontium in the carbonates. And we could then divide the curve of strontium isotope in the carbonates into 4 intervals. However, we noticed that in the lower 2 intervals, the strontium isotope in the carbonates are way too high than our impactite end members, suggesting there may be additional inflow end member in the catchment. To find out this unexpected end member, we again take a look at the risk criteria catchment. If the inflow lake waters were dominated by, if the inflow waters were dominated by surface waters, then waters would largely leach the Bonte breccia at the terrace zone and solivite in the central crater, but both of which are low in strontium isotope ratios. The crosses here are the basement rocks, and the 2 humps in the middle are the uplifted inner ring structure. We found that the only possible pathway to deliver high strontium isotope ratio inflow into the lake is by this red arrow shown here, which is upwelling groundwater flow through the crystalline basement. Then we could explain our 4 strontium isotope intervals as shown in the carbonates. The first interval, we require both crystalline basement groundwater and surface runoff on the solivite to explain the high strontium isotope in our carbonates. The corresponding lacustrine lithofacies of the earliest lake deposit is within this inner ring, as also shown by this small red line here. It was a small lake catchment, and we suggest that the earliest lake water was likely to affected by the hydrothermal activity due to the presence of the hot solivite or impact melt pool in the central crater. In the next stage, to explain the strontium isotope decrease in the carbonates, we suggest increasing inflow from a shallower groundwater aquifer at the equator margin. Except for its lower strontium isotope ratios, additional evidence to support this aquifer to be an inflow source is that we observed spring mount carbonate directly developed on top of this unit. In the next step is characterized by the lowest strontium isotope ratios in the carbonate of 0.7104. This is almost perfectly explained by the massive inflows that is derived from the Bonte breccia, which has a quite close strontium isotope signature of 0.7101. We noticed that the distribution of the lacustrine fishes as indicated by the cyan line here, had greatly expanded to the crater margin than the previous small lake era as shown by the red line. And the last step to account for the increase in the strontium isotope ratios, we attribute this increase to an exotic inflow that is derived from a specific sedimentary formation called Opaninustone. The only outcrop of this formation is located at outside of the northeastern crater rim. This would suggest the inflow most likely completely incised the crater rim at the northeastern side. Our edge models suggest that it took almost 1 million years to 1.4 million years from the time of the impact to the formation of a completely incised channel on the crater rim. And what is our implication to the Mars? On the Mars, we have numerous craters, and these craters listed here have a similar size to the Rhees with a diameter of 20 to 30 kilometers. But from left to right, they show increasingly degraded crater rim. At the last crater here, it has an inlet at the eastern side, which is completely incised its crater rim. So we're wondering if it also requires about approximately 1 million years to 1.4 million years on Mars conditions for fluvial lacustrine activity to cause similar landscapes. And here is the synthesis of the different hydrological pathways and its evolutions at the Rhees crater. In the beginning, we have hydrothermal groundwater upwelling through the inner ring. And as the crater cooled down, we have increasing groundwater and runoff accumulated from the crater rim to the central lake. And lastly, as the fluvial lacustrine activity goes on, we finally have a completely incised river channel that is developed on the crater rim. The whole process only takes for 1.4 million years. Thank you for your attention.
All right, thank you very much. I'll go ahead and invite all 4 of our speakers to please come to the front. And we have 20 minutes for questions from the audience. When you come up to the mic, please a reminder to state your name and affiliation. We're monitoring online.
Wendy Calvin, University of Nevada, Reno. I have 2 questions. The first is for Joe. The wetting makes stuff look really dark. And so I didn't catch from the videos if things as they dry out actually get bright again. And so I'm wondering if there's a way you could combine the darkening as a proxy also for wetting, as well as the presence of a 1.5 absorption feature.
That is the absolutely wild thing, is when you're in the field, that surface looks dark and damp. And so the detectability with the RGB sort of color data is inconsistent with what the spectrometer is seeing. So dark pixels are not always the best way to identify water, even though obviously they are wet on Earth. But
right.
I think
or an albedo change maybe, and then once you see that transition, it stays dark, and so you can say that's a proxy that it got wet and we saw it get wet. I don't know.
yeah, I think that's probably the way to look at it. So yeah, folding in the RGB data is a great idea.
Yeah. And the other question then is for Emmy, and I wanted to make sure that I understand what you're measuring in the field. I think you said you're measuring XRF in the field. Are you also measuring Raman in the field?
Yeah, I should have said this. So both of those techniques and our V-near infrared data is all in situ in the field.
Okay.
Yeah, because this stuff changes, hydration states so quickly. We really wanted to prioritize doing it in situ.
Exactly. So I was going to say, if you were taking stuff back to the lab, how are you preserving it? But you're
Right.
doing all of this in the
Yeah.
field at the time. Okay,
Right,
great.
right,
Thank you.
right.
Kate Hendrickson, Rutgers University. I have a question for Emmy because we talked a little bit about this yesterday, and I'm really interested in this magnesium precipitation for the calcium and these gypsum minerals and what that might mean for site substitution. Do you have an idea in these cycles where you're substituting magnesium in, where the calcium's going? Do you have a little bit of a bigger picture on what's going on there? Because obviously it's a full cycle process, and if we're gonna analyze it, I don't know, together at some point, I was just wondering where you were on that as a baseline.
No, this is a great question. I don't have an idea at this time. I'm actually sort of generally a little bit, it's interesting to see what happens seasonally to the calcium writ large. It's very clearly kind of efflorescing on the muds in the evaporative period. And then in the wintertime, it appears to sort of go away. So, even if you are looking at those same muds in those same locations and sampling from there, it's very hard to detect high calcium. So there's some process of transportation. It's relatively insoluble, so it's difficult to think, what exactly is doing that transportation. So something to, I think, investigate further, but I don't have a great answer for that. I also have been wondering if it's just adsorption, because you see this kind of sulfur increase as well. So teasing apart that difference, I think, is like something I'd really like to work on.
Yeah, and in it, like, there could be some sort of interlayer capture
Yeah.
stuff, and so
Yeah,
very interesting.
yeah.
But a follow up to that, I couldn't quite follow the timeline for the field work. Was this like one summer and one winter, or have you seen this like full cyclically, and do you see the reverse happening on the weather with the weather changes? Sorry, I'm not very good at saying words in your people's world. I'm like, minerals, that's like all I got. Sorry.
Yeah, no. So we've gone 6 times now, 3 times in the fall and 3 times in the winter. So we are able to see exactly that, progressing from drying to freezing, from freezing to drying, et cetera. And this situation of kind of the changing abundance of calcium, it's a little bit variable. The first year we didn't see as many definitive crystals, I don't think. But broadly speaking, that trend of higher identifiability in the fall and then kind of this loss is preserved through those 6 seasons. So yeah, changing annually. Yeah.
Okay, awesome. Thank you.
Thank you.
I steal the mic and so to steal the mic briefly and kind of piggyback on what you were saying and maybe give Wendy a fuller answer to your question. One of the really interesting things about a lot of these analog environments is the sort of deliquescence efflorescence cycle that we're seeing. And I guess what's surprising to me about the Alvord, which I did not anticipate, was that there is a transitional phase between, you've dissolved the salts and the surface is dark and damp, and then you would expect the next transition would be to bright and dry. But there's something in between where it's dry, but the hydrology hasn't delivered a sufficient amount of salty brine to actually build up an efflorescent salt crust. And so there's a sort of seasonal variation. There's a sort of time of day variation. So all of these sites are telling us that time really matters. And that's, I think, a very cool set of observations to put together.
Thank you as well.
Dan Mason, University of New Mexico. Question for Joe. You briefly touched on this during your talk, but I'm curious if you could elaborate a bit more on how the fieldwork you did in Oregon might compare to other RSL analog sites. I'm curious specifically about the various water tracks and wet patches that we see throughout the dry valleys.
We've flown this push broom spectrometer on both Antarctic Dry Valleys water tracks and in the Alvord Desert. And broadly, again, this absorption feature is really robust, obviously, and so you can see soil moisture distributions. What we have here in the Alvord Desert, which is really novel, is that time of day observation. So we have sort of just a series of moisture maps across the dry valleys, and they tell the same story. Not just that time matters, but also space. So again, there's not a uniform albedo distribution across shallow groundwater plumes in the cold desert. They're drier at the edges and they get wetter and wetter towards the core with some internal variability. So any place you see sort of meandering or braiding of an albedo feature, it's a strong piece of evidence that water might be involved.
Thank you.
Susanne Schwenzer, the Open University, with a question for the Reese crater. And I should probably say, as a background, I got my PhD in Germany and I visited there a couple of times. And I know that they always had difficulty finding the mineralogical evidence of the hydrothermal system, although we all suspected it was there. It's a little bit in the cores, in chloride and that kind of thing. So have you been able to connect your strontium data and the various hypotheses or the various evidence from where these waters come to a broader mineralogy and the temperature indications that might give?
Yeah, thank you for your question. That is a great question. And I think at the Reese crater, of course, like Gordon Osinski or other authors had done those mineralogical studies very extensively. But to my impression, at the Reese, because we have these materials for really precise geochemical analysis, the evidence to support those deposits to be hydrothermal could be derived from strontium isotope, of course, and there is carbon and oxygen isotopes. Some of these carbonates, they show really depleted oxygen isotopes, which point to higher temperature at the time of the fluid forming. And if there are quite specific mineral associations, I think carbonate could be one of them. And there are, in the central peak, we observed some mound-like stuff that is quite specific for hydrothermal mound. It's also calcium carbonate. And hope that answered your question.
Thank you. I have to go back.
Hi, I'm Mike Malaska from JPL Caltech. I do have a question for Joe. Have you seen any time variation in the microwave data? And you'd also just touched on it just a second ago where you were talking about, the deliquescence, efflorescence, which presumably would do all sorts of wild, funky things to the dielectric constant of salts too.
I'm sure it is there. I've not dug into it enough. So what you saw there in the sort of quick time lapse was 2 sets of flights over 2 days. And so there is quite a bit of heterogeneity. And the big question, I think, is, are we seeing hydrological heterogeneity? Are we seeing salts? Any kind of EM method for measuring soil moisture is going to be very sensitive to salt. And this is, again, a very salty plume. So I think it's something to look for. You might expect to see sort of a halo if you're depositing salts around the edges, sort of anomalously high apparent soil moisture. We tend to see it at the core, though. So I guess my gut instinct would be that it's not going to dominate the microwave data, but it's absolutely something we're going to look for next.
Do you see any correlation or anti-correlation with respect to the IR data?
That I didn't do before this LPSC, but I will do it after. Thank you.
Mike Thorpe, UMD and NASA Goddard. Question for Taylor. First point, you didn't have time to play it, but it was the best video ever. So can you tell me what that video?
I'm kind of biased. It's very similar to Joe's, in which the lake we were at, I was sampling the salt with the spectrometer that Emmy has used as well. We're both from Georgia Tech, and it's James's spectrometer, James Ray's. And I was taking a spectra, and then the rangers that I was with, because everybody else was at a different lake, because I was really interested in all the mineralogy in this lake. And all of a sudden they're like, the water's moving. And I was like, what are you talking about? And I couldn't move fast enough. I couldn't sample fast enough because the groundwater was coming in so fast. So it basically doubled the lake in size in the matter of, I would say, minutes. So I'm a little biased as to why that video, because I probably took it, but yeah, it was really cool to see in person.
Cool. Well, so then a follow-up question on just your research in general. So you have 2 fundamentally different water sources there, like the groundwater and the lake water. Do you see, I don't know if you took sediments or anything at depth to see is there a weathering front when that's percolating, the lake water is percolating through mixing in the subsurface? Because we see that in some places.
Yeah, it's a great question. So unfortunately, we did not do a lot of at depth. I would say in this paper, some of the limitations is that we didn't do enough shallow groundwater stuff and actually sampling more at depth, what's happening in the subsurface. But I didn't really mention this, but we also are trying to understand the microbial influence on the iron and sulfur cycling in these areas, because they're pretty dominant. And so we will talk about that in the paper as well, but I didn't have time either to talk. Yeah.
Cool. That would be pretty interesting if you go back there to sample at depth.
Yeah, I agree.
Thank you. We can work on that.
Liz Rampy, NASA JSC. I have another question for Taylor related to Mike's question. So you're seeing in some of these lakes, they are sourced from acidic groundwaters and some are sourced from basic.
Yeah, those 2 different catchments that I showed had 2 different groundwater sources. Yes.
Okay.
Are you asking why that may be?
No, but
okay. No, sorry, I could totally let you finish. I was just gonna say part of it is geological. They do have different, one is like more felsic and mafic composition. The other is granitic rock. And I will say the ones that are more near neutral, which is that Cam Paleo Valley Channel, it also had like belts of greenstone really close to that area. So we're thinking there's also, that was also why that there is more near neutral in that area.
Okay, cool. My question is, is there anything that could be preserved in the rock record that tells us whether that groundwater that sourced the lakes was originally acidic or basic?
Not for basic. I would say for acidic, those profiles that I showed that were more truncated and exposed. So those are like the lateritic profiles that are described in Western Australia, and they do like I kind of go in depth in this paper about like what features you're actually seeing that are acidic, because there's like smears and streaks that are from like goethite, hematite, and they're formed through like these acidic groundwater interactions and like exposures. So yeah, more acidic, not I don't have enough probably info to say anything about interactions with like basic groundwaters.
Okay, thanks, Taylor.
Thank you for your question.
I'll ask another question to Taylor. On the theme of temporal changes, you made a comment, ask me about Lake Gunter and the wet to dry season and the cool variations that happen.
Yeah, I mean, I will say, kind of go off it. It was the most extreme also because it had like groundwaters at depth were near neutral, and we were like not expecting it to change so drastically. And it's the first lake that's been described in these settings as having like magnesium chloride brine. And so we were like, is this coming from the groundwater? You know, is this why we were getting like higher concentrations of magnesium or calcium? And so we've looked at the groundwater bores in that area. They're not as well studied in that specific area. So we have thoughts about going back and sampling those. But from all of the groundwaters, like across Western Australia, none of them show like high concentrations of magnesium or calcium calcium. And so if you like plot that on this like type of spider web, you'll see that the only things that have like higher magnesium concentrations are lake water. So we think it's definitely just from evaporation. Yeah, sorry. I mean, there's probably more to that whole story with Lake Gunter. It's also the only lake that doesn't have like low cell activity. So we're kind of like looking at all the microbial stuff as well.
Awesome. Thank you. I actually have another question for Emmy about these magnesium substituted gypsums, which sounds really cool. And I've never heard of, but on Mars, we found at least currently with Curiosity, we're finding a lot of co-occurrences of gypsum and magnesium sulfate. So I'm wondering, is this something that we've seen on Mars? Could we even see it on Mars with our instrumentation? How do they compare?
Yeah, I think that's a really good question. You know, in the sulfate unit at Gale, I feel like at least with ChemCam, which is mostly what I'm looking at, you see these kind of distinct, you know, pockets of magnesium sulfates and calcium sulfates even within the same rock that are kind of, you know, separated from each other on a micron scale. So it doesn't seem, you know, the lack of kind of correlatedly enriched magnesium and calcium in the same Lipps point strikes me as like not an obvious, you know, not the same process potentially as what we're seeing here in these lakes. I've actually been wondering if Kemin would be useful for this in terms of site substitution. And okay, great. So yeah, maybe Kemin would be the best way of really kind of verifying if this is happening in Gale route. Yeah, so would be cool to see it.
That's cool. Or is the lack of not seeing it also telling you something?
I think so. Yeah, I think, you know, the way we've been thinking about this unit, at least the way I've been thinking about it is this a big multi-component brine that's sort of been seeping in and then, you know, evaporating out this kind of process of the chemical divide set of salts. And that I think certainly could still be the case here rather than kind of this, you know, system that's really broadly enriched in magnesium sulfate that was, I don't know, had a little bit of calcium in it. I think maybe we really did have a lot more calcium in the solution because this is kind of clearly coming out of solution and not showing this enriched magnesium. But I don't know, I'd have to think about it a little bit further to sort of use this as an end member case for Gale. And I'm definitely wanting to do that. So yeah.
Hello, Bum-Soo Kim from NASA Johnson Space Center. I have a question for the fourth speaker. So very nice talk. It's very interesting to see, you combine all geochemical and to look at the geologic setting and beyond to Mars, right? So my question, I have two questions. First question is, well, it's like 20 to 30 kilometers crater, right? So on other craters on Earth, how does it, the strontium behave or, correlate with the geologic, does the size matter, like in terms of the dynamic? Like in different craters, do you see similar or very different?
Yeah, that's a good question. And unfortunately, we don't have enough data for other craters because this crater is really well preserved. And I guess the problem is most of those impact crater lake deposits were possibly not preserved. I know Halden crater may preserve lake deposits, but so far these data have not been analyzed with strontium isotopes.
Okay, yeah, cool. And second is just from my curiosity. So 2030 seems very big, and it's right at the mid-Miocene. And then from my curiosity, since I did paleoceanography, did it have an impact on the climate change of the mid-Miocene climate optimum? Are you?
The setting is post mid-Miocene climate optimum, and so the correct term is mid-Miocene climate transition. But I assume that this setting is considered consistently warm and wet if you would compare to any Mars conditions.
Oh, okay, cool. Thank you.
Thank you for your question.
Yeah.
All right. Well, thank you everyone once again, and thank you very much to our speakers. All right, we're going to jump over to Ocean Worlds now, where Morgan Cable will be presenting on cold water soda geysers as Ocean World analogs, investigation of habitability indicators pre and post eruption.
Hello, everyone. Thank you so much for the opportunity to be able to speak about this today on behalf of my amazing team of co-authors here. And yeah, I'm going to, and I realized I should have brought a bottle of soda. That would have been quite appropriate. But yeah, our solar system hosts a diversity of ocean worlds and dynamic worlds, some of which have evidence for plume activity. Triton, Enceladus, and Europa being some of our top examples here. And when it comes to these plumes, they can be sourced potentially, in the case of Europa, possibly from sort of near surface reservoirs trapped in the ice, potentially deeper down as well, leaving deposits on the surface that we can have amazing opportunities to study and explore with missions like Clipper. For Enceladus, we were very fortunate to have Cassini be able to collect not just remote sensing, but in situ observations by doing multiple fly-throughs of plume material. And so at least in this case, we do have some pretty strong evidence for that plume being sourced from that subsurface liquid water ocean that is in contact with the rocky interior of that moon. But even with all of the data of Cassini, we still have multiple models that fit our observations. Some of them involve sort of shallow boiling interfaces, deeper boiling interfaces with a nozzle. More recently, Carl Mitchell and Jason Rabinovich have been able to also study and explore volatile exsolution as a way of moving material from that subsurface ocean or reservoir and having it expressed via a plume. Now, right now, we can't distinguish between any of these models, and it's important because depending on the eruption mechanism, the mechanics behind that, we may end up with enrichment or depletion of certain, say, habitability indicators or even biosignatures. And so really by understanding the mechanics of how that eruption takes place gives us a better idea of how to trace back any measurements that we make of the plume material or surface deposits to its host reservoir. And since we're not going to get any new data, at least not until Clipper arrives in the Jovian system in 2030, what can we do in the meantime? Well, we can look to some Earth analogs. And I hope to convince you in the next 8 or so minutes today that smack dab in the middle of Utah is actually a place where I think you might be able to draw some parallels to some of these eruption mechanics happening at Ocean World. So these are soda geysers. They're part of this Green River aquifer system. And you may imagine geysers as typically being, produced by boiling, so heating. But in these cases, these are actually due to CO2 enriched brine at depth mixing with meteoric water, which leads to supersaturation. You end up with volatile exsolution and buoyant acceleration, and basically the same thing that happens if you shake a bottle of soda and then crack it open. Now, there are about 10 different natural aquifers that are all connected to the same host reservoir, and they vary in size. Most of them are human drilled. These two in particular that I'll be talking about today are, you have Crystal Geyser on the left, which was from an exploration well drilled a while ago. It used to erupt on the order of like 20 meters high, but eruptions nowadays tend to be bimodal and range on the order of a few meters, like you could see here, to up to 5 meters. Champagne Geyser is a much smaller borehole, about 3 centimeters in diameter. It still can reach some pretty decent heights, but by studying both of these that are connected to the same aquifer system, obviously they have different eruption energies and cross sections and eruption volumes. We were hoping to get a better understanding of how you can connect pre and post erupted materials and see if there's any of this enrichment or depletion in a natural system. And so we were very grateful to be funded, and we were able to support 2 students through the Europa Clipper Icons program. So we had 2 students. Kate Kraft brought Isabella Musto from Denison University, and I was able to bring Elizabeth Kirby from College of Charleston. And we collected samples both for chemical analysis as well as biological analyses. I'm only going to talk about the chemistry today, but I definitely encourage you to continue to follow the reports of this team. And so we collected erupted effluent as the eruptions were occurring, as well as we were able to pump things out from these boreholes and these wells. And I want to be clear that this is different from the actual aquifer, the host reservoir, which is, hundreds of meters down. So really, we're just looking at pre versus post erupted material very close to the surface. And what did we find? We found a few interesting things. One measurement that we were able to make right away in the field was conductivity, which is a proxy for salinity. And we found that in both of these geyser systems, the erupted material had higher conductivity than unerupted. And you may think, duh, Morgan, why are you showing me this? Of course, you have volatiles and evaporation happening. So of course, things are going to be a little bit more concentrated in the erupted stuff. Well, it turns out it's actually a little bit more complicated than that. We did some water chemistry analyses. And so in these plots, the blue is erupted for both geysers and the orange is the unerupted. And what we found was that some salt concentrations stayed the same. It was actually mostly the monovalent cations and anions, so sodium and chloride, that had relative concentration differences between what was erupted and what wasn't. And so what we actually think is going on is that this CO2 enriched brine that starts at depth, it's denser than the meteoric water that sort of sits on top of the aquifer in the system. And so what's happening during eruption is you're getting better mixing of those. And so you're pulling in more of that sodium chloride enriched waters that are sourced from deeper down. We also were interested in understanding what happens when this material is deposited on a surface. And so we looked at 2 different types of samples, one that we're calling evaporites, and then I'll also show you some flash frozen effluent as well. So we just took some of this, the erupted material or unerupted material, the waters, let them just dry out on some microscope slides. And then we use Raman spectroscopy just because that's a technique that's readily available to us in the lab. And I should point out that Raman and IR reflectance are complementary techniques. They're both sort of remote sensing spectroscopic techniques, but there are some features in certain absorbances that are different in those systems. Some are Raman active, some are IR active. And what we noticed was we actually saw some differences in the evaporites for both of these geysers. For Crystal, which is the larger geyser that had the very large borehole, about 40 centimeters in diameter, we saw that this was a lot more carbonate rich, calcium carbonate, mostly aragonite and calcite. And for the chemists in the room, those are the orthorhombic and trigonal polymorphs of calcium carbonate. But then for the smaller geyser, Champagne, we saw this was actually enriched in sulfate minerals, things like glauberite. So it was interesting that even though they're sourced from the same host reservoir, ultimately deep down in that aquifer, that we're getting expression of different materials in that dried evaporite that could presumably be some sort of deposit, plume deposit on a surface. Interestingly, we also took some of that erupted effluent, and we just did this for Champagne geysers. This is sort of still in the preliminary stages. We took some of that erupted geyser water, and then we froze it down to 75 Kelvin, so Europa or Enceladus relevant surface temperatures, and put it under vacuum. And then when we did those measurements, instead of seeing, sodium and calcium sulfate rich minerals, we saw something that looked almost exclusively like vitreous magnesium sulfate, which was very interesting to us because, now, of course, we're not going to see sodium chloride in Raman spectra. Most of those transitions are spin forbidden, so you don't see them in Raman. But we were surprised to see this difference between just the dried evaporite and the frozen aqueous ice. And I think this is a good lesson in reminding us all that when you are doing measurement techniques, it's important to collect multiple sort of in situ and remote sensing pieces and form that full picture of the material that you're trying to understand. So, do these make good ocean world analogs? In some respects, yes, but of course there is no perfect analog for a geysering system here on Earth. Crystal Geyser, though, does seem to have some parallels that make it a closer analog for Enceladus. You have this exsolution of CO2. We've seen CO2 in Enceladus's plume, high levels of sodium chloride, sodium bicarb, and then the evaporite materials were rich in carbonates, whereas with Champagne, the smaller geyser, this one had more enriched sulfate minerals in the evaporites. And again, we saw that vitreous magnesium sulfate in the frozen effluent. So this is just the start, but there are a couple of lessons that I think perhaps we might be able to apply when we're exploring these active ocean worlds in our solar system. It does seem that, there's a combination of eruptive energy, proximity to the host reservoir. These may all play a role. We do seem to see evidence consistent with eruptions being able to source more deeply and well-mixed waters from that host reservoir, wherever it may be. So that could tell us that when it comes to sourcing or studying geysers and plumes of other ocean worlds, you really want to target the big places, so sample there. And also, again, making sure that you understand and are able to integrate observations both from in situ measurements as well as remote sensing. And I mentioned earlier that this was supported through the Europa Clipper Icons program. We're really grateful to them for funding, as well as a lot of our friends and colleagues in Utah for letting us collect these samples. And I went pretty fast. No, I'm right on time. Look at that.
Yes, thank
Amazing.
you so
Thank
much. Super cool. Thank you. All right. Our next speaker will be Jennifer Witten, talking about Veritas Iceland 2023 Field Campaign, Initial Synthetic Aperture Radar Results.
All right. Hello, everyone. I'm very pleased to be here to talk to you about some of the Veritas field results that we're just starting to get in. This is a field campaign that we did in 2023, and we're starting to look at these FSAR results just now. So as a reminder, the field campaign was largely inspired by trying to figure out how to analyze these lava flows and better understand what we might be seeing with the Veritas mission on Venus. So these data were collected in collaboration with DLR. This is their FSAR instrument. We collected at multiple wavelengths. So X and S are of particular interest to us because the Veritas mission will be collecting data at X band. Magellan data are at S band, and the Envision mission will also be collecting data at S band. So better understanding how we map flows and what characteristics of flows we are actually mapping is of vital importance to understand prior to getting these data for Venus. Alrighty, so we had 3 field sites. We were looking at flows at Fagradalsfjall, which has had recent eruptions in the early 2020s, kind of over the last handful of years. Askja, which has had lava flows. The most recent ones were in the 1960s, but sort of 1870s and even before that. And then the Holaron flows as well. which were erupted between 2014 and 2015. Alrighty, so jumping right into it, I recruited several team members to use the full resolution FSAR data. So these data are at 2 meters per pixel. I'll get back to that a little bit later in the talk. I requested that people map at 1 to 2000 resolution, which they may or may not have want to thank me for in the end. But that left us with the final map resolution of 1 to 8K. Most people digitized in ArcGIS or QGIS. Again, it was on the full resolution FSAR data. And I asked people to map at X and S band to see if there were any variations in their boundary definition. And we wanted to start with no machine learning. I did not let them use image data. This was like, hey, we're getting Venus data. You have no idea what you're looking at. Go draw some lines. So it's a very humbling exercise, to say the least. And the major question we had here is just, are there major differences in the boundary identification between these frequency bands? In surveying all of the mappers, there were several criteria that were consistently used to identify what we are calling flow boundaries. We could, I guess, have a discussion on nomenclature and sort of the parts of lava flows and flow fields, but differences in texture. And what I mean by that is shown in this bottom right image here. There are 2 orange arrows. I'm not sure if you can see them, but this portion appears more consistent in its sort of DN values and its brightness. And then down here, you can see it's much more mottled. There's a lot more bright and dark pixels mixed together. So differences in texture were used. We also used adjacent near parallel pairing of bright and dark pixels, which is shown in the bottom left. You can see that interior to the flow here, but also along the periphery in a lot of cases. And then lastly, one of the major criterion used were broad differences in brightness. So over here on the top right, you can see that you have sort of mid-tone gray here and a lot more dark pixels over here. And so these were the basic criteria that all 6 of the mappers used in mapping flow boundaries. This is the first site. I'm going to kind of flip through these fairly quickly, but this is the data for the Askia area, the Ficaron flow, which was erupted in the 1960s. This is a really cool site. There's a lot of sediment superposed on these flows, so we get to experiment not only with the roughness of the lava flows, sort of based on the eruption textures, but also post-emplacement processes as well. Here are the lines drawn by our 2 mappers. These are 2 different greens, just to give you a sense. For the most part, people agreed. Their level of ambition was slightly different between all of the mappers, I will say. But these are the flows I was most interested in anyway, so it didn't really matter. So some people mapped in more detail and not, but those boundaries were very easily identified. Here, Askia. Here is the visible imagery. This is at 15 meters per pixel, so a little bit lower resolution, but you can see that these lines generally match brightness variations, and a lot of them are associated with flow or sediment boundaries. Here is the Holaron flow. This is more kind of in central Iceland highlands. The map lines are drawn in both pink and blue over here. And what I hope is very striking is you don't see a lot of lines on the inside. And that's because despite the variation in surface textures, which is demonstrated by this facies map that Joanna Voigt produced in 2021, there are rubbly, spiny, shelly, pahoehoe textures that we see all throughout Holaron. But the only place that we found lines or boundaries are actually associated with plateaus. So it looks like topography is really like large variations in topography are what are driving our boundary identifications. And last, this is a Fagradalsfjall. So this is on the Reykjanes Peninsula. These are the eruptions that have been occurring from 2021 through today. This image is, from this visible image is from a little bit earlier. You can see we map flows up here, and there were in fact flows there when we were there. This is just a 2022 image instead of a 2023 image. But I want to zoom in to this area right here to show you my humbling personal experience. This is a lava pond. This is the S-band. We did the VV polarization. Here are the lines. You can see that kind of broad variations in pixel brightness were largely used in identifying boundaries here, as well as some textural differences. But both mappers mapped right here. And that is a hillside. And when you go back, you're like, oh yes, of course. Of course, this is different. There's a boundary right there. But if you don't know that, you don't identify that. So this has been very informative to better understand kind of what are the controls on the pixel brightness values, sort of the backscatter that we're seeing, and the boundaries. And before I get too far ahead of myself here, I also want to show you, this is X and S band boundaries that were drawn by the same mapper. Just to give you a sense for differences, the exterior boundaries were largely consistent. It was mostly the internal boundaries where we're identifying variations in brightness or texture, and the interior of the flows, and that is most different. So here's the X band radar data, just to give you a sense here, where these yellow lines were drawn, and I'm going to take the lines off and try to flip back and forth so you can see here that there is this somewhat more distinct boundary in the X band as compared to the S band. So we're largely finding our results are largely consistent with some of the work that Catherine Niche has done, for example, trying to analyze the radar textures of lava flows to figure out if we can identify different flow textures using backscatter properties. All right, let me keep going here. And this is the S band. So if you want to just see, I'm going to flip back and forth real quick to see those subtle differences in texture. And we're very interested in being able to identify differences and understand what's an actual difference versus a textural difference, because change detection on Venus is very important. We do expect that there is some amount of change detection on the surface between when the Magellan mission imaged in the early 90s and today. Especially given that there was obvious change detected over the course of the Magellan mission by Robbie Herrick and Scott Hensley just recently. So I'm putting up my conclusions here. This is just the start of this project, but what we can see is that a substantial amount of detail, the individual flows are difficult to identify, the different textures are difficult to identify, and we're really only identifying differences internally if there is sharp changes in topography or really large differences in sediment cover. So in that Askia region, there was in some cases 10 centimeters of tephra sediment deposit or even more. And so that was really allowing us to detect these variations in the lava flow roughness. And that right now we're seeing minimal variations at the Fagerström between X and S. And just real quick, we're going to start doing this mapping at Veritas and Magellan-like resolutions. So here's what we mapped. Here's the Veritas, and there's the Magellan that so that'll be a quicker mapping experiment for sure.
All right, thank you very much.
Thank you.
All right, our next presenter is remote, so we'll change the slides for you in here. So just let us know next slide. It will be Dan Nunez, who will be talking, continuing with the Veritas campaign, but telling us about initial results on permittivity measurements of the Veritas 2023 Iceland Analog Campaign site.
Thank you, Abby.
Dan, I
Can
have
you hear me?
the clicker. Yes.
Excellent. So next slide. So thanks, Jenny, for introducing to the audience the campaign that we had. And one thing that I would like to recall at this point is that the backscatter, the radar backscatter that we observe in a radar image depends not only on the properties of the radar that is illuminating the surface, but also on intrinsic properties of the surface, such as the slopes created by regional or local topography, the roughness of the surface at the wavelength scale of the radar, and variations in the shallow subsurface, such as fine scale layering and inhomogeneities that could exist. And these all are affecting the backscatter. So in the end, what we want to do is look at a radar image such as this Reykjanes Peninsula FSAR flight line that we collected and understand what is actually controlling the brightness of the radar, why this is this one area with the arrow darker than the other areas that we see. So, and here's just for background, the properties of the basic parameters of the radar used in Magellan, the ones to be used Veritas and Envision. So next slide. Going on the theme of lava flows, so following Jenny, here we see some high radar backscatter lava flows in Ubastat Fluctus, and which are surrounded by volcanic plains. And the inset here, you see this boundary between the radar bright lava flow and the radar dark lava plains or volcanic plains. So why is there such a contrast? Is this surface roughness? Is this some other aspect? And what we're going to concentrate on this presentation is the analysis of permittivity. Next. Now, Jenny showed these two beautiful images from the Iceland Askja 1961 volcanic flows, Vikaran volcanic flows, which has this radar bright lava flow with respect to the surrounding terrains. At the top is the S-band process to look like Magellan, and the bottom is the X-band process to look like the 30-meter Veritas. So quite a bit of improvement in quality going from Magellan to what we're going to attain with Veritas. And the scale of these images is similar to the inset from the previous slides. So next. During the campaign, we not only had the overflights from DLR's FSAR system, but on the ground, we collect a variety of data to constrain and ground truth what we were going to see in the radar images. One of the things that we did was collect in situ permittivity probe data. We had one probe available, and we were only, of course, able to collect data in soils because the probe cannot be inserted into rocks. And that kind of restricted the number of the ground control patches that we study in terms of probe data. But still, we collected a total of 200 total measurements with the permittivity probe. We also collected every control patch, sediments and rocks, and we packaged them at the field to preserve the moisture content. And so we could analyze them in the laboratory. And moisture is very important because it does also control the radar backscatter. The higher the moisture content, the higher the permittivity, therefore the higher the radar reflectivity. So next. The task that we're aiming to do with the permittivity effort is to determine the moisture content, both in situ and in the laboratory, and this has been completed here at JPL. We're shooting to determine the grain size distribution of the different samples, the soil samples. This is being done at DLR by our colleagues. Permittivity measurements of the soils and rocks is ongoing here at JPL, and the team is going to use these data to do forward modeling and help invert the radar backscatter data. Next. So here's an example of a site just adjacent to the Halaron lava flow. This is a sedimentary unit where you have a pebbly lag at the surface in right beneath it, sands, volcanic sands. So here on the left, we see the probe inserted into the ground, as well as the sample collection tube. And the extreme of this left image, you see the trench. And on the right image, we see the trench itself. And the stars denote the places that we collected permittivity and samples, permittivity with the probe and samples. And we can see that this yellow bar right next to the tape measure indicates the penetration of the probe. And this top unit appears to be brown, a little bit more brown or yellowish in color than the deeper portions of the trench. The trench was about 20 centimeters deep. And this denotes a variation in composition of the soil. Later on, we're going to see some analysis of permittivity, and we're going to look at the data from this top yellower unit and the bottom darker unit of this range. Next. So looking at the results for moisture content at the sites, these were collected with a probe concurrently with the overflights of the radar. So we were constraining the moisture content at the time the radar images were collected. And for the most part, the dielectric constant, the real part of the complex permittivity range in the, between 5 and 23. You see some areas here in the top histogram where the real part is going to mid-80s. Transitioning to the mid-80s, and these are data from going from a margin into the water of a nearby stream. So we use the water as a calibration point. The imaginary part is there as well. The stream water being higher, there's some ions dissolved in the water, increasing its conductivity. And in the lab, we found moisture contents in the soils between as high as 25 to 30% weight percent. If you jump to the next slide, we'll see that there's we also collected compositional data for some of the samples in the laboratory, because especially the iron and titanium content control the imaginary part of the complex permittivity, and this is the loss term. This is what determines how deeply the radar signal is penetrating into the subsurface. So these XRF data were collected at the University of Massachusetts Amherst via our colleague Darby Dyer and Michael Wallinger. And we can see here in this graph of titanium plus iron versus silica that the samples can be divided into two end members here, the more silicic and the more mafic. So we're going to look at permittivity later on for some of these. Now, if you go to the next slide, you see that the moisture content tend to be higher for the more silicic samples. So the higher the bars here, for example, sample number 4 with weight percent of about 26, 27, corresponds to sample 4 here in the compositional plot. So the more silicic samples, they were a little bit more moist despite differences in location and collection times. So my interpretation is that the clays in the sample are tending to hold on to the water. Next.
We have about a minute left.
Yes. Here's one of the deeper in the train. This is the top of that trench, the sample wet straight out of the sample tube. Next. Here's it dried on the top and the center. It has two components, a more yellow and a darker. We sieved, and you can see the two components. Next. And here are them loaded into the sample holders for the permittivity analysis. We are able to pack them at different densities. And we packed also the two end members, the finer and the coarser. You can see the difference in color as well. So next. Here are one of the rock samples, which we sawed, and next, and cored to produce the cores to analyze the permittivity of those. Next. And here are the permittivity results from our samples. The ones at lower density are the soils, and the high density ones are the cores. The grays and white dots are from the literature. The curves are empirical models. And the greatest sensitivity of permittivity, especially the real part on the left, is to density. So you see the greater the increase in density, the higher the real part. These are the color diamonds here for different samples. If we look at the stars, these are the corresponding samples that were collected, the permittivity values collected at the field, so they were moist, while the permittivity results from the lab, they were after the samples were dried at 50 Celsius for a number of days. And on the left are the imaginary part of the permittivity showing the control of moisture. There's a small dependence on temperature as well, and this is part of a PDART effort that is going on the site to understand the effects of Venus temperature. So let's go to the last slide.
Great, thanks. And we're at time, so.
Okay, so density and no surprises there. And we're going to be using these results with our radar analysis effort.
Wonderful. Thank you very much.
Thank you.
All right, our final speaker will be Zachary Morse, giving us an overview of the 2024 Augmented Reality Data Visualization Analog Research Campaign, AARDVARC, Analog Lunar Rover Development.
Thank you very much. And thank you to everybody here for sticking around for one last talk. I'm Zach, and this is some information about our P-STAR project that is ongoing. And so to kick off the last talk, we'll start things off with a bit of a bang, which I've always wanted to do. This is July of 1967 in a field outside of Flagstaff, Arizona. NASA and the USGS collaborated to set off a series of explosions, which is not something we get to do today, but we get to benefit from it. They essentially were creating what is now called the Cinder Lake Crater Field. It was based off of this lunar orbiter image, which they had at that time of the lunar surface, and they were trying to recreate a 1-to-1 scale section of desert. This is an aerial photograph that they got afterwards, where they could practice for the Apollo missions. And this will show them side by side. They were very careful to set them off with the amount of explosive to replicate the size of the craters and also time them so that the ejecta overlapped appropriately. And so this is a really cool analog environment that they used for training. They did some lunar lander sims. They did a lot of the training for the driving of the lunar rover there and testing out some new designs as well. And then it sort of fell into disuse. It was fenced off and not really used by many projects until last October, when our team got to be the first NASA field team to go back out there in almost 50 years. So what is the AARDVARC project? You may have seen this slide or a slide like it at this conference or other ones, the general Artemis timeline. And the premise of AARDVARC is to see what data could be collected by one of these early precursor robotic assets, a lander or rover getting to the lunar surface, that could then help augment when humans arrive for a sustained human presence on the lunar surface. So in our case, we were testing a rover design that collected imagery, some compositional data, and LiDAR data. The LiDAR data being key to give you high resolution topographic information for the surface. The idea being that when we go back out this May, we'll have volunteer human astronauts who will wear heads-up displays with augmented reality data visualization that will do terrain-based navigation and in-situ data visualization. And to make it even more complicated, we wanted to simulate lunar south polar lighting conditions. So we did our analogs at night at the crater field with the lighting system that was developed by JSC for the Artemis training. So it's a bright light that shines off into the distance, and it's on a tripod that's calibrated to be approximately what you would get with the sun just a few degrees above the horizon at the lunar south pole. And that results in these really interesting scenes where you have very, very dark shadows that extend down sun. And the interior craters are kind of difficult to see, but then if you turn around and look up sun, it's very blinding. It's similar to what I imagine you would feel if you were at the lunar south pole. So for this October, we had a rover deployment. This is our rover. It's called the Husky rover. It was provided by our friends at Mission Control Space Services up in Canada. It had a few instruments mounted to it, including 2 cameras. One was a point tilt zoom camera, or PTZ, capable of zooming on specific targets that the science team wanted to look at. It had a front-facing navigational camera that always pointed right in front of the rover so they could see where they were driving. And they got imagery back in near real time, sort of like you would get for the moon. Perhaps most importantly, we mounted a LiDAR scanner on top. This is a Leica BLK 360 scanner, which is capable of giving you topographic information of lower or about a centimeter up to 10 meters away from the scanner itself. And then last but not least, we simulated having an XRF unit, although this was not attached to the rover. We simulated a rover arm. We had volunteers, in this case, Jared, who's in the audience, acted as the rover arm to collect XRF data when the science team drove up to a rock and wanted some information. And so here's a good quick video. You see the rover driving. This is about the speed it traversed the field site. And this is Riley, one of our field team members. He is not operating the rover. He is monitoring its systems and making sure it's safe, ready to hit the emergency stop if the mission control team accidentally hit the rim of a crater or a rock or something. And speaking of, this is actually controlled by a team of mostly students at the University of Texas, El Paso, led by Dr. Jose Hurtado, who went above and beyond to set up not 1, but 2 different mission control setups at UTEP. And you can see they're having a good time, but they did a great job of simulating the environment of a mission control, hands-on experience, which is great to pass along. And they made all the science decisions based on some criteria that we gave them ahead of time, as well as some pre-mission remote sensing data that we provided. Oh, we also had a small team at NASA Goddard. So not only were we divided or having remote operations, but those were split between 2 different remote operation centers. So we had 3 different time zones going on, and it was a lot of practice. Microsoft Teams did a lot of heavy lifting for us, but it worked out really well. So this was our initial traverse plan for the rover. We used a small section of the crater field site, but the primary idea was to have the rover traverse primarily east and west. And you can kind of see that small triangle at the top. Our lights were always pointed towards the south. So most of our traversing was perpendicular to sun direction, so that it makes it a little bit easier to navigate, although we included sections to specifically test if you drove up sun or down sun, how difficult that would be. And this was designed to get maximum coverage of the LiDAR. Ideally, the rover would drive a few meters, pause, collect imagery and LiDAR data. It would be returned to the mission control team in near real time. They could analyze it and continue traversing. And this is a sample of our LiDAR data. Every green cube you see is a location where the rover paused to collect that data, and the cube roughly represents the rover's orientation. You see a few trees, you kind of blank those out in your mind or overprint those with an HLS. They're about the same size. But the craters are pretty well visible, also ignoring the small shrubs. But the mission control team did a great job of navigating the craters in such a way that they didn't drive into them, but also got scans into the interior of those craters. So we have a pretty full coverage of that field site to use for our next step. And as a quick example here, this is 2 of our panoramic images stitched together. It's pretty dark. You can see the sun in the distance in the top right. And if we blow that up, blow up the exposure, you can kind of see you're on the rim of a big crater, but you're looking into the shadowed region, so it's very hard to see with just your passive imagery. They also collected LiDAR from the same location, and you can reveal a lot more detail in there. You can see some tire tracks, some shrubs. And so this is just to show that having an active sensor like a LiDAR really helps in these extreme lighting conditions. And so the next step, we're going to try and plug all of this into a couple Apple Vision Pro heads-up displays. This is for this May. We're targeting to go back to the field. And essentially, we take our digital terrain model using some software called Merit, or the Mixed Reality Exploration Toolkit developed at NASA Goddard, viewed through the Apple Vision Pro. So essentially, you will see the world as it appears around you. The units have cameras and LiDARs to sense where they are relative to that model, or in this case, the field. And we should be able to overlay visual cues, such as navigational directions, or identify a specific rock that the rover may have looked at and guide the astronauts. We'll be doing some testing to see how this might offload their cognitive load and help them conduct field activities. So getting closer to some conclusions. So far, with just the rover deployment, we were able to draw some conclusions sort of based on the analog objectives for Artemis, or AOA-SAT. One of which, objective D2, was to assess what instruments do you want to send to the moon. And in our case, I think we make a strong case that the active sensor, the LiDAR, is valuable when you're navigating. Sometimes if you're driving, depending on sun angle, that LiDAR actually really helps for both navigation and scientific return. Speaking of driving, objectives E from the AOA-SAT all deal with complex lighting environments. So we found, no big surprise, driving perpendicular to sun, that was great. You could really see the terrain in front of you. Driving down sun was okay, but you start to lose some of the detail in the shadows. And driving up sun was really difficult. Given the dynamic range of our navigational cameras, it tended to blow out images and make it a bit more difficult to navigate. And finally, there is an objective about remotely distributed mission control rooms. And we found that with really strict comms discipline and some careful training, we were able to manage. I think it is, based on our recent experience of years of remote meetings on Microsoft Teams, but with good audio and good audio descriptions of what's going on, we were able to manage pretty well. And thanks to Jose and his leadership at UTEP. So I kind of want to draw to a conclusion with this image. It might be a little hard to see in this lighting, but this is a drone image we got during the test at night. So our lighting is at the top. It's casting shadows down towards the south. Bonus points if anyone can find the rover in this image, but it is great. It, I think, evokes the lunar South Pole pretty well, and the rover is actually there. It's that little dot casting a shadow at the rim of the crater. And what makes this image really interesting is near the bottom, you can just make out some wheel tracks. And those are actually very faint. If you go there during the day, they're pretty hard to see, but given this low angle lighting, they stand out in this image. And we're pretty sure that those were left by the rover training vehicle by the Apollo astronauts. So this is one image that sort of links pre-Artemis training and pre-Apollo training in one image, which is really fun. And so, yeah, I'll just thank the whole team. This is actually my first time being the PI of a major project. So without everybody on this list, it would not have been possible, especially the students from UTEP. And in the last 30 seconds, I know that we as a community are entering some uncertain times. And so I would just ask that we continue to hold that door open for the next generation of scientists. This is sort of my opportunity to pay forward experiences I had in grad school. So yeah, keep doing that no matter what happens, if we're here next year or not. And special thanks to the USGS Astrogeology Center and the Coconino National Forest for facilitating access to the field site. And with that, I'll end with 5 seconds left. Thank you.
All right, I think you know the drill, but I'll invite all 4 speakers to please come up to the front, and we'll open the mics for questions. It's 3 speakers. All right.
Hello, this is Colin Wilson, European Space Agency. A question for Jenny Whitten. I love the flow field mapping. Have you had a peek yet or plans to look at as whether polarization helps you map the flows?
We are planning on doing that, but this is as far as we got. We were hoping to get a little bit further, but yes, polarization is something that we're planning on looking into as well.
Great, thanks.
Hey, Dan Malowich, Cornell University. I also have a question for Jenny. You showed what you called your humbling experience of mapping the side of a hill slope.
Yeah.
You would expect that to be like different material roughness and even local slope. So what happened? How does it look the same?
Yeah, I have not had the chance to go look at that in too much detail. We don't have high resolution LiDAR. So in addition to the synthetic aperture radar, we had the in situ measurements. There is an Iceland like 2 meter per pixel DEM, which we could take a look at, but we don't have the high resolution data at that particular point to do some finer comparisons.
Yes, as somebody who studies Titan.
Yeah.
As someone who studies Titan, that scared me. So.
Yeah, no, it was, as I said, humbling, and because I knew that we wouldn't, get all the interior flow margins, but the exterior margin was a little rough.
Hi, Joe Levy, Colgate University. I had a geyser question for Morgan. So that you described really nicely the pre-eruptive versus post-eruptive chemistry. And I was wondering, what about like aerosols and really fine droplets kind of blowing away? What kind of fractionation would you expect, or biological differences, or would you want to try and catch that aerosol on slides with a drone? Just hypothetically.
Absolutely. Yeah, and I believe others like Connor Nixon have had a chance to go to Iceland and do some measurements of the geysering systems there, which are thermal. But that's certainly follow-on work. This was kind of a preliminary study. We're grateful to the ICONS program for helping us cobble together enough money for the 4 of us to go out there for a week. But certainly that would be a future aspect we could take it in. So if you have a drone or have some friends who have one that want to come out to the middle of Utah, I will gladly meet you there.
Yes and yes.
Hi, Alexandra Mathieu Novak from Johns Hopkins Applied Physics Lab. I had a question for Zach. Your project's super cool, and I'm glad you got funded to do it. I'm curious how you're going to integrate your XRD data. Was it XRF?
XRF.
Sorry, how you're going to integrate your XRF data with your environment, and also 2 questions. Do you consider trying to integrate orbital data? Because we have so much orbital data of the moon, and I think it would be really useful to see if you can kind of make those comparisons of how orbital data could be useful in your environment as well.
Yeah, I'll answer those in reverse. The lunar data idea, because this field site is actually a replica of a section of the moon, we actually have real lunar data that corresponds to this section of the Arizona desert. So we do plan to do that. The resolution might be pretty high, but we're hoping to sort of project a blanket of large pixels and then have astronauts walk from one to another and make observations to see what they see. The next test is more focused on the ops question. So even if the science, if they see no change, that's still a valid observation that we're trying to get them to give. For the XRF data, we're working on that now. Ideally, we might do some smaller EVAs around the boulder field. Everything here is sort of human made, so it's not a natural setting, obviously, but they placed a bunch of boulders out there, which the rover was able to scan. And so if we do some tight EVAs around those, we could have a visual of the graph, a ternary diagram, something that shows up that shows the data from that XRF, and then potentially ask the astronauts to try and rescan with a handheld instrument that same thing the rover tested to see if there's any change. So yeah, different con ops we're testing out, but hopefully something works like that.
Hi, Gerard, Imperial College. My question is for Dan. That was a wonderful campaign you showed. I have two questions. One briefly is, I didn't understand whether you sampled soils in the patches you mentioned. I would like to know whether you also took samples or are considering analyzing samples from the lava fields themselves, like in Askia and Holoroyn. And my second question is, with the analysis you already have, like these global pictures of your sites, can you relate whether these results that you're getting align with what we have in perhaps what we would expect on Venus? So does that align with this analog looks like maybe a good target after all?
Yeah. So yeah, we collected both soils and rocks, and we're doing analysis on all of them. The soils and the rocks were dried, and we calculated the moisture content of both. Now the soils were collected not in the patches themselves. We defined a patch and we preserved this the patch pristine because we were having the radar doing the imaging about concurrently with the collection. So we didn't want to alter the surface properties at the wavelength of especially X band. So, but we collected the samples adjacent to the patches in a way that was representative of what the material was in the patches. The results are controlled mostly by density and moisture. And in terms of the soils, especially moisture. So that's unlike Venus, but that was the whole point of collecting the soils and preserving that their moisture with the packaging, so we could understand how much moisture was playing an effect on the radar backscatter, because that's something we're not going to see on Venus. So we don't want to overinterpret things in our radar data extrapolating to Venus, for example. Now, in one of the figures in the slide, the last figure with the results, there was the results for the core, where we elevated the core temperature to Venus-like, and there is a dependence on temperature of permittivity, and this is coming up on a paper that we're writing here at JPL currently. And so overall, I think the results are similar to what we're gonna see on Venus. Broadly speaking, each area of Venus is gonna have its own particularities. But the key thing that we're doing here with this campaign and analysis is to decompose all of the different effects of the surface properties and how they're contributing together to form the radar backscatter we see in the image. So once we do that, when we start attaining understanding of that on a setting, on a volcanic setting that is analog to Venus in terms of lava flows, then we're going to be able to take these lessons and apply to interpretation of Veritas data once we start receiving data from the mission.
Sure. Thank you. Thank you.
Hi, my name is Arij. I have a question for Zach. Like, since you simulated like both the lunar landing site and the mission control so well, I was wondering if you guys like tried to simulate any of like the I guess like any of the aspects of communication between mission control and the astronauts on the moon. And mainly like what I'm wondering about is like the 3-second communication delay between Earth and the moon. Did you guys take that into account? Like, did you put the guys in mission control on like a 3-second communication delay?
That's a great question. We didn't specifically do that for the purposes of this test. We were seeing if it was even possible. We in the field, we were actually using a Starlink Mini to send things to the internet, and so there was inherently a bit of a delay in just getting things from the field in Arizona back to UTEP. I don't know if it was 3 seconds, but it was near real time. It certainly wasn't instantaneous. And as we go forward to the astronaut deployment, we might try and simulate at least a smaller mission control with a bit of a communication delay and see how the augmented reality does help with data visualization and command visualization, that kind of thing. But yeah, for this part, it was an inherent delay, but we're not exactly sure what it was.
Okay, thank you.
Thanks.
Can I build off that question? I was just very interested in the LiDAR and how long it took to collect a scan and then send a scan and then have the team and mission control analyze it and then make decisions about where to go next.
It's a great question. So the scanner itself is able to do its scan in under 4 minutes. So it's a pretty quick scan in the field. The behind the scenes, so the folks operating the rover never saw this, but we had a field team out there who would then downlink that data to an iPad and then uplink it to a Google Drive, which simulated the rover just automatically doing it. That process, because the file was so large, took between 10 to 15 minutes of just of downlink time, and then there was additional minutes at the other end. The team at Goddard actually started being the ones to sync those scans together, and there was a quick quality check. Usually after each scan was available, it was noted in the software from Mission Control Space Services. There's a light that would come on that said LiDAR available, and we could do a quick quality check to make sure that the scan hadn't failed, and then sort of continue the traverse while it was being analyzed. So sort of lots of overlap in the timeline.
I have a question, if I can jump in, Abby Freeman from JPL for Morgan about plumes. And I was just wondering if you could go over again the reasoning for one of your conclusions, which I think is fascinating, that there were differences in the evaporites coming out from the plumes, even though they had the same source region, and why that happened. And then what are the implications for when you fly through a plume in Enceladus and you want to use that data to interpret the composition of the subsurface ocean?
Yeah, we aren't 100% sure because if you look at the water chemistry analyses, the sulfate concentrations, for example, were just about identical for all of the samples. We did notice, and I didn't get a chance in that brief presentation to talk about it, the samples when we collected them were crystal clear, but within about 20 minutes, you could see a precipitate form. And this happened whether we refrigerated them or not, or put them on ice or not, whether we had, sealed them really tightly to sort of preserve the headspace or not. And so we think, obviously, there is some precipitation happening. We think as the CO2 is exsolvating out, you see this with like aragonite and other things, that precipitate also had depending on sort of when we collected it in the course of the eruption would have sort of an orangish color versus a more whitish color. So we are seeing different minerals, like presumably some iron rich minerals as well. And so I think there is definitely going to be more work to go in understanding those relationships between immediate collection, how you preserve the sample, and as well as what one of the other questions came up with, where you do that collection, right? The sample volume you're able to get and sort of those heterogeneous or surface chemistry properties of things that can happen as you get to smaller and smaller, particle sizes. So yeah, long story short, not sure.
Bumsukin from Johnson Space Center. Thank you all for the great talk and a question to Zach. But first of all, thank you very much for the last kind words. I know it's a very crazy time right now, but also I've been to many field trips, but it was one of the sexiest field trip and work, I think, for doing this kind of research. But my question is, so I study asteroid and meteorites, but apologize for my naive background, but so if your lander will go on the moon and with these very good LiDAR work, what is needed for, is it possible if we just land right now and then is the LiDAR option available, or do we need more like payloads or like satellites to do that?
It's a great question. The LiDAR, so the exact unit we were using is not space ready, but there are space ready LiDARs. I think a lot of the commercial landers use some form of LiDAR or photogrammetry to assess a safe landing spot as they come in. So even just getting that close, it's higher resolution than you get from orbit. And so for the AR visualization we're aiming for, you need pretty high resolution so that when you're in situ, you know, you're not the unit can track better. So yes, I think it's definitely possible, and there are units available.
Okay.
We're just waiting for more data.
Cool. Thank you. Yeah. Can I ask one more question for Morgan? I think ocean water really excites me. So I was wondering, you know, if the Europa Clipper is, you know, passing by this plume, but I imagine from your site work, is it possible to also sample the sprays? Did you do the spray or sampling, or because I imagine, you know, if it's plume, if you're not right direct at the plume, then some of the sprays will be more, you know, a direct evidence to actually see what we can see on the Clipper, right?
Yeah, that is a great question. So with Cassini at Enceladus, which gravity is, 0.01, 1% Earth's gravity, plume material gets lofted pretty high. At Europa, the gravity is greater, so a lot of the larger particles may not get lofted very high, but we know that there are micrometeoroid impacts happening all the time, and the PI for the SUDA instrument on Clipper is in the room if he wants to jump up and say a few more things here. But essentially, any sort of plume deposits or other things that are on the surface that'll get exposed to that will loft material high enough that Europa Clipper will be able to fly through it and sample it. And the surface dust analyzer on Clipper is specifically designed for each ice grain or dust particle impact. You get a mass spectrum. So we'll get a really nice set of analyses of the composition of various parts of the surface. And Sasha has done some work to trace those particles to specific places on the surface. So you will also get a compositional map that comes from that.
Cool. Thank you.
Yeah. Did I get a thumbs up, Sasha? Did I do a good job? Okay, thanks.
And I'll give it 10, 15 seconds for any final thoughts or questions here.
Can we thank our organizers in those 15 seconds for doing such a great job of putting together a great session?
That's fantastic. Well, I didn't do anything. Thank you. Thank you to everybody at LPI and everybody on the program committee. This was really fun. So whoever put this session together, thank you.
And the remote.
And thanks to everyone
worked
for
really
sticking
well.
it out.
Yeah. All right. Well, we're at 11:25. So I think this is declaring it officially the end of LPSC 2025. As a reminder, Dwornik judges. Dwornik judges, please turn in your scores. And thank you everybody so much for coming. It's been so great seeing you all. And enjoy the rest of your day. Thank you.
Safe travels, everyone. Take care. And thank you, tech team. You guys did a great job too.
Thank you very much to all of our tech team.